Every detail in this story comes from real scientific research and observation. There is a place in the solar system where the wind moves faster than the speed of sound on Earth. Not on a gas giant, not near the sun, at the very edge of everything, on a planet so far from the sun that the sun itself, seen from its surface, would look like nothing more than an unusually bright star. The wind there reaches 600 meters per second. That is more than 2,000 kilometers per hour. And no one has ever been there. A moon orbits that planet right now, a moon moving in the wrong direction. Every other large moon in the solar system orbits in the same direction its planet rotates. This one does not. It moves backward against everything, like something that arrived from somewhere else and was caught before it could escape. It is covered in geysers. At -235 degrees Celsius, the coldest measured surface in the solar system, something is erupting. Nitrogen gas, driven by nothing more than the faint warmth of a sun 4.5 billion kilometers away, punches 8 kilometers straight up into an atmosphere so thin it barely exists. That moon is falling. Not quickly, not in any way a human civilization could perceive, but the mathematics are exact and the outcome is certain. In approximately 350 million years, tidal forces will pull it apart. It will cease to exist as a world. Its material will spread into a ring, a structure more massive than anything Saturn currently possesses. A planet will gain a ring system. A moon will end. The process is already underway. This planet was found by mathematics before anyone ever looked for it. Two astronomers, working separately, predicted its existence by measuring the way it was pulling on a planet they could see. The prediction was so precise that when a telescope was finally pointed at the right location in the sky, the planet appeared within 1 degree of where the equations said it would be. That was 1846. Since then, only one spacecraft has ever visited. It arrived in August of 1989, traveling at over 15 kilometers per second. It had been flying for 12 years. The window of closest approach lasted hours. The data it returned, the images, the measurements, the discoveries, came back to Earth at the speed of light, a journey of more than 4 billion kilometers. Then the spacecraft kept going. It is still going now, and no other mission has followed. No orbiter, no lander, no probe sent specifically to study this place. In the entire history of human spaceflight, one flyby is all that has ever happened. Everything known about this world, the wind speeds, the geysers, the backward moon, the rings, the storms, comes from that single pass. 48 hours of data. One chance. Tonight, that is where this story goes. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail you are about to hear comes from real scientific research and observation, grounded in decades of measurement, calculation, and the data returned by the only spacecraft ever to reach this place. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. The solar system has 8 planets. Most people can name them. Most people have a rough sense of scale. Mercury close to the Sun, then Venus, then Earth, then Mars, then a gap, then Jupiter and Saturn with their rings, then 2 more planets in the outer dark. Those last two are called Uranus and Neptune. And in almost every illustration, every poster, every classroom model, they are shown as roughly equal, two blue balls at the edge of things, similar in size, similarly distant, similarly cold and strange. But the distance is not intuitive until the numbers are stated plainly. Earth orbits the Sun at an average distance of approximately 150 million kilometers. That number has a name, one astronomical unit, abbreviated AU. It is the standard measure of distance within the solar system. Jupiter is 5 AU from the Sun. Saturn is 10. Uranus is 19. Neptune is 30. 30 times the distance from Earth to the Sun. In kilometers, that is approximately 4.5 billion. Light, traveling at 299,000 kilometers per second, takes 8 minutes and 20 seconds to reach Earth from the Sun. From the Sun to Neptune, that same light takes 4 hours and 9 minutes. A radio signal travels that same distance, and any response takes equally long to return. A simple exchange of messages requires more than 8 hours of waiting. When Voyager 2 flew past Neptune in 1989, and scientists on the ground made a small adjustment to the spacecraft's camera angle, they had to send the command and then wait, knowing it would be hours before the adjustment happened, and hours more before any confirmation arrived. This is the distance at which Neptune exists. It is not simply far. It is far in a way that changes the nature of interaction. Every measurement Voyager 2 returned felt like a letter from another world, because it was. Neptune was the last planet discovered in the classical sense. Mercury, Venus, Mars, Jupiter, and Saturn have been known since antiquity, visible to the naked eye, tracked across the sky by ancient astronomers, thousands of years before telescopes existed. Uranus was discovered in 1781 by William Herschel, who initially mistook it for a comet before its circular orbit revealed it as a planet. Neptune was different. After Uranus was discovered, astronomers tracked its orbit carefully over the following decades. Something was wrong. Uranus was not moving exactly where Newton's laws of gravity predicted it should. Its orbit was being perturbed, pulled slightly off course by something unseen. In the 1840s, two mathematicians independently began working on the same problem. Urbain Le Verrier in France and John Couch Adams in England both began calculating from the observed deviations in Uranus's orbit where an unknown planet would have to be in order to cause those exact perturbations. They worked separately, using the same gravitational principles, arriving at similar predictions. Le Verrier completed his calculations first and sent them to the Berlin Observatory. On September 23, 1846, astronomer Johann Galle received Le Verrier's letter, and that same night turned a telescope to the predicted location. Within less than an hour of searching, he found it, a small blue-green disk, clearly not a star, located within 1 degree of Le Verrier's predicted position. Neptune had been found by pure mathematics. No one had looked for it. No one had seen it. It had been calculated into existence from the gravitational footprint it left on its neighbor. This was one of the great confirmations in the history of science, a demonstration that Newton's laws of gravity, applied with sufficient precision to observational data, could reveal the unseen. It established a principle that would later be used to predict the existence of other bodies, to measure the masses of distant stars, and eventually to infer the presence of objects that no telescope can directly observe. The planet was named Neptune after the Roman god of the sea, in keeping with the tradition of naming planets for classical deities. The blue-green color that would later be confirmed by spacecraft, caused by methane in the upper atmosphere absorbing red light and reflecting blue, seemed appropriate for a planet named for the ocean. For the next century and a half, Neptune remained a point of light. Even the largest ground-based telescopes of the 19th and early 20th centuries could resolve it only as a small disk, its features indistinct, its moons difficult to observe. The largest moon, Triton, was discovered just 17 days after Neptune itself on October 10, 1846, by British astronomer William Lassell. He noted that it was unusually bright for a moon of an outer planet, and that its orbit appeared to run in the opposite direction from Neptune's rotation, a retrograde orbit, anomalous and unexplained. That anomaly would not be seriously examined for more than a century. What telescopes eventually established about Neptune in the decades following its discovery was limited. It was approximately the same size as Uranus. It had at least one moon, and its blue color distinguished it from the other outer planets. The interior was largely unknown. The atmosphere was largely unknown. The surface of its moon was entirely unknown. It would take Voyager 2 to change that. Neptune is classified as an ice giant. This is a distinct category from the gas giants Jupiter and Saturn, though the distinction is not always intuitive. Jupiter and Saturn are composed primarily of hydrogen and helium, the lightest elements, in proportions that are not fundamentally different from the Sun itself. They are enormous balls of gas, compressed to liquid and plasma states in their interiors by the weight of their own mass, with no solid surface at any point. Neptune is different in composition. Its interior is dominated by a mixture of water, ammonia, and methane, compounds that are gases at room temperature and pressure on Earth, but exist in exotic states deep inside Neptune, under pressures and temperatures that have no equivalent in ordinary experience. These materials are sometimes collectively called ices, not because they are cold in the familiar sense, but because they are the compounds that existed as ice in the early solar system before they were incorporated into a forming planet. Beneath that mantle of exotic compressed material sits a rocky core, estimated to be roughly the mass of Earth, compressed to a diameter perhaps slightly larger than Earth's. The core is probably not a sharp boundary. The transition from rocky material to the ice mantle above it likely occurs gradually through a zone of mixed composition where rock and high-pressure compounds are intermingled. Above the mantle, the atmosphere begins. Neptune's atmosphere is composed primarily of hydrogen and helium, about 80% hydrogen, 19% helium, with approximately 1% methane and trace amounts of other compounds. The methane in the upper atmosphere absorbs red wavelengths of sunlight and reflects blue, giving Neptune its vivid blue color. But the color is not the remarkable thing about Neptune's atmosphere. The remarkable thing is what moves inside it. Neptune receives roughly 900 times less solar energy than Earth. At 4.5 billion kilometers from the Sun, the sunlight that reaches it is faint, a tiny fraction of the energy that drives Earth's weather systems, ocean currents, and seasonal cycles. By any straightforward reasoning, a planet receiving so little energy should be a calm, cold, nearly static world. Neptune is not calm. It is the most dynamically active atmosphere in the solar system. The winds in Neptune's atmosphere reach speeds of up to 600 meters per second near the equator, approximately 2,100 kilometers per hour, or about 1,300 miles per hour. For comparison, the strongest winds ever recorded on Earth's surface during a hurricane or tornado reach roughly 140 meters per second. Neptune's atmospheric winds are more than 4 times faster than the strongest winds ever measured on Earth. The Great Red Spot on Jupiter, the most famous storm in the solar system, sustains winds of approximately 150 meters per second. Neptune's winds are 4 times faster than that. The question of why Neptune has such violent atmospheric dynamics, given its distance from the Sun and its correspondingly low solar energy input, is one of the outstanding problems in planetary science. One part of the answer lies in Neptune's internal heat. Unlike Earth, which has cooled significantly since its formation and radiates only slightly more heat than it receives from the Sun, Neptune emits approximately 2.6 times more energy than it receives from the Sun. It is generating heat from within. The source of that internal heat is not fully understood. One hypothesis is that the planet is still contracting under its own gravity. The same gravitational compression that heated it during its formation continues to release energy as the planet contracts infinitesimally over geological time. Another possibility involves the differentiation of heavier materials sinking toward the core, releasing gravitational potential energy as heat. There is a third hypothesis, more exotic and more difficult to test, that involves the behavior of methane under extreme pressure. Deep inside Neptune, where pressures reach millions of atmospheres and temperatures may reach thousands of degrees Celsius, methane molecules are thought to be broken apart. The carbon and hydrogen atoms separate. The hydrogen rises toward the surface, and the carbon, under the extraordinary pressure, is compressed into a different form, diamond. Experimental evidence from laboratory studies using high-powered lasers to simulate interior planetary conditions has shown that methane can be converted to this crystalline structure under pressures equivalent to those found deep inside Neptune. The diamonds that form are believed to sink through the interior toward the core, releasing gravitational energy as they fall, contributing to the internal heat that then drives the atmosphere. It may be raining diamonds inside Neptune right now. This is not confirmed. The interior of Neptune cannot be directly sampled or observed, but the experimental and theoretical evidence is considered credible enough that it appears in mainstream planetary science literature and has been studied at facilities, including the SLAC National Accelerator Laboratory. The atmosphere above all of this is driven in part by this internal heat rising upward, creating convective motion, driving circulation patterns, producing the extreme wind speeds that Voyager 2's instruments measured in 1989. Neptune also has a magnetic field. It is a strong field, roughly 27 times more powerful than Earth's, but it is unusual in its orientation. On Earth, the magnetic axis is tilted roughly 11 degrees from the rotational axis. On Neptune, the magnetic axis is tilted approximately 47 degrees from the rotational axis, and the center of the magnetic field is offset from the planet's geometric center by more than half the planet's radius. This means Neptune's magnetic field is not generated symmetrically from the core, as Earth's is. It appears to be generated in a conducting layer partway through the mantle, likely the layer of ionic water and ammonia, where conditions allow electrical currents to flow and generate a magnetic field through a dynamo mechanism. The result is a magnetic field that wobbles dramatically as Neptune rotates, creating a complex and asymmetric magnetosphere that sweeps through space in a way unlike any other planet in the solar system. Neptune rotates on its axis once every 16 hours and 6 minutes, faster than Earth but slower than Jupiter or Saturn. Its axial tilt is 28.3 degrees, close to Earth's 23.5 degrees, which means Neptune experiences seasons in a familiar sense, though each Neptune season lasts approximately 40 years, because a full orbit around the Sun takes 164.8 Earth years. Neptune completed its first full orbit since its discovery in 2011, 164 years after Gally first saw it through his telescope in Berlin. In that time, human civilization had changed beyond recognition. Neptune had completed one lap around the Sun. The outer solar system operates on timescales that make human history seem momentary. Standing at the edge of the solar system, if standing were possible, the Sun would appear as a star, brilliant compared to other stars certainly, but a star nonetheless. A single point of light. Its warmth would be undetectable, its color would be white-yellow, indistinguishable from other bright stars in the sky. In every direction there would be darkness. And slowly in that darkness, something would be moving overhead. Not a star, not quite. Something with a surface. Something with geysers firing upward through a thin shell of nitrogen atmosphere into the near vacuum above. Something orbiting in the wrong direction for reasons that go back to the early chaos of the solar system's formation. That is Triton. And its story is different from everything else in this system. The 14 moons of Neptune are mostly small, irregular bodies, captured objects or debris left over from the formation of the planet itself. They have names drawn from Greek and Roman mythology associated with the sea: Naiad, Thalassa, Despina, Galatea, Larissa, Proteus, Hippocamp, discovered as recently as 2013 from Earth-based observations, making it one of the smallest known moons in the solar system. But none of them are Triton. Triton accounts for more than 99% of all the mass orbiting Neptune. Every other moon, every ring particle, every captured fragment combined makes up less than 1% of the total. Triton is not one moon among many. It is the dominant body, and everything else exists in its shadow. Its diameter is approximately 2,700 kilometers, larger than the dwarf planet Pluto, larger than the asteroid Ceres, larger than most moons in the outer solar system. It is the 7th largest moon in the entire solar system, ranking alongside bodies like Europa, Titania, and Oberon that are worlds in their own right. And it is in the wrong orbit. Every moon in the solar system that formed alongside its parent planet orbits in what is called a prograde direction, the same direction the planet rotates. This is a consequence of angular momentum conserved from the original disk of material from which both the planet and its moons formed. When a solar system forms, the disk rotates in a consistent direction, and the objects that coalesce from it inherit that rotation. Triton orbits in the opposite direction. It moves retrograde, counter to Neptune's rotation, counter to the motion of every other body in the system, counter to the implied history of its origin. There is only one explanation consistent with orbital mechanics, and the known physics of solar system formation. Triton did not form here. It came from somewhere else, and Neptune caught it. The where and the how and what happened when the capture occurred. These questions carry answers that reach back 4.5 billion years to a solar system that looked nothing like the one that exists today. The planets were not where they are now. The orbits were not stable. Material was moving, colliding, being scattered outward and inward in a period of reorganization so violent that its traces are still visible in the craters of every rocky body in the inner solar system. In that chaos, something remarkable happened at the outer edge of everything. A world that had been drifting in the cold beyond the planets encountered a giant. And the giant held on. The temperatures on Triton's surface sit at 235 degrees below 0 Celsius. That is 38 degrees above absolute zero, the theoretical minimum temperature at which all molecular motion would cease. Triton is not quite at absolute zero, but it is closer to that limit than to any temperature experienced anywhere on Earth, including the deepest Antarctic winter. At those temperatures, nitrogen, which forms most of Earth's atmosphere as a gas, exists on Triton's surface as ice. The surface is covered in it, bright, reflective nitrogen ice, mixed with methane ice that has been altered by radiation from the sun and from Neptune's magnetic environment into a pink-tinted residue of complex organic compounds. The surface of Triton in images returned by Voyager 2 appears pinkish white, with a texture unlike any other moon in the solar system, smooth in some regions, chaotically jumbled in others, marked by a distinctive pattern of rounded depressions and ridges that planetary scientists named cantaloupe terrain for its resemblance to the surface of a melon. Nothing else in the solar system looks like it. The origin of the cantaloupe terrain is not fully understood. The leading hypothesis involves a process called diaporism, the slow upwelling of warmer, less dense material from beneath a colder, denser surface layer. On Earth, salt diapers form when underground salt deposits, lighter than the surrounding rock, push upward through the crust over millions of years. On Triton, a similar process involving nitrogen or methane compounds rising through a denser crust of water ice may have produced the distinctive surface texture. If so, the interior of Triton was once warm enough, or remains warm enough in deep layers, to drive slow convective processes that reshape the surface over geological timescales. Triton is not simply a frozen dead rock at the edge of the solar system. Something inside it has been, and perhaps still is, active. The evidence for that activity sits on the surface in one of the most unexpected discoveries of the Voyager 2 mission. Dark streaks. Running across Triton's southern polar cap, a bright, reflective region covered in nitrogen ice, deposited over millennia of seasonal frost cycles, are long, dark smears. They extend downwind for distances of up to 150 kilometers. They are consistent in orientation, all aligned in the same direction, suggesting they were all formed by the same mechanism and the same prevailing winds. They are the remnants of eruptions. Not volcanic eruptions in the conventional sense, not lava, not ash, not the silicate rock material that erupts from volcanoes on Earth or Io, but eruptions nonetheless. Plumes of dark, nitrogen-rich material carried upward from the surface and then blown downwind before falling back. Triton has geysers. At 235 degrees below 0 Celsius, in the coldest environment in the solar system, something is erupting from the surface and punching upward through the near vacuum above. The mechanism that drives these geysers is itself a remarkable piece of physics, one that depends not on internal heat, but on sunlight. How sunlight, arriving at Triton so faint that it provides less than 1,000th of the energy it provides to Earth, can power active eruptions on the coldest surface in the solar system, is a question with a precise and elegant answer. That answer is where this story continues. The nitrogen ice on Triton's surface is transparent, not opaque like the ice on a frozen lake, not cloudy like packed snow, transparent, clear enough that sunlight passes through it, entering the ice and traveling downward into the layer below. The layer below is dark. Dark material absorbs light. Dark material converts light to heat. In the vacuum of space, where there is no air to carry heat away from a surface, absorbed light builds up, slowly over days and weeks, raising the temperature of whatever has absorbed it. The dark substrate beneath Triton's transparent nitrogen ice absorbs sunlight. It warms. The nitrogen ice directly above it, heated from below rather than from above, begins to sublimate, transitioning directly from solid to gas without passing through a liquid phase, because at Triton's surface pressure, liquid nitrogen cannot exist. The gas pressure builds within the ice layer, and then it finds a weakness, a crack, a thin spot, a place where the ice above is fractured or insufficiently thick. The pressurized nitrogen gas erupts upward through the opening, carrying dark material with it, the same dark substrate that absorbed the sunlight and started the process. The geyser erupts high into the sky, measured by Voyager 2 at 8 kilometers altitude. The dark material disperses into Triton's thin atmosphere and is carried downwind by the prevailing winds, settling eventually on the surface as a dark streak, the streaks that Voyager 2 photographed and that planetary scientists studying the images in 1989 recognized immediately as evidence of active surface processes. This mechanism is called solid-state greenhouse warming. The transparent nitrogen ice acts as the glass of a greenhouse, allowing sunlight to pass through and reach the absorbing layer below, while trapping the resulting heat rather than allowing it to radiate back into space. The same principle that warms a greenhouse on Earth, scaled down to operate on a frozen moon at the edge of the solar system with 1,000 times less sunlight. It is one of the most counterintuitive processes in planetary science. The coldest surface in the solar system is erupting because of sunlight. The sunlight arriving at Triton is so faint that at midday, at the equator, it provides roughly 1,000th of the solar energy that reaches Earth's surface at noon. This is not enough energy to warm Triton's surface appreciably. The global average temperature remains at that extreme minimum, but it is enough, concentrated by the greenhouse effect within the ice layer, to trigger the phase transition in the nitrogen directly above the absorbing material. The geysers are not continuous. They appear to be seasonal, most active during Triton's southern summer, when the south polar cap is tilted toward the sun and receives the maximum available sunlight. Voyager 2 arrived during a period of southern summer on Triton, which is why the dark streaks and active plumes were concentrated near the South Pole. The northern hemisphere was in winter during the flyby. Whatever processes may occur there during northern summer remain unobserved. Triton's atmosphere is thin to a degree that requires careful qualification. Surface atmospheric pressure on Earth is approximately 1,000 hectopascals. On Mars, it is roughly 600 pascals, less than 1% of Earth's. On Triton, surface pressure is approximately 1.4 pascals. That is less than 1/70th of 1% of Earth's surface pressure. It is a near vacuum by any practical measure. But it is not a complete vacuum. The atmosphere exists. It has structure, a troposphere, a stratosphere, a thermosphere. It supports hazes at altitudes of 5 to 10 kilometers. It carries the dark material from the geysers downwind and deposits it in characteristic streaks. It interacts with Neptune's magnetosphere in ways that Voyager 2's instruments detected and measured. The atmosphere is composed almost entirely of nitrogen, the same gas that makes up 78% of Earth's atmosphere. The nitrogen sublimates from the polar caps during summer, enters the atmosphere, migrates toward the winter hemisphere where it refreezes, and the cycle continues. This gives Triton a seasonal atmospheric cycle that, despite the vastly different scale and temperature, operates on the same general principles as Earth's water cycle. Nitrogen evaporates in summer. It snows in winter. The polar cap that receives sunlight shrinks. The polar cap in shadow grows. The cycle operates over timescales of decades, not months, because Triton's orbital period around Neptune is approximately 5.9 Earth days, but the full seasonal cycle is governed by Neptune's orbital period around the Sun, 164.8 years. Triton also has a thin haze layer in its lower atmosphere. The haze is not composed of water droplets, as Earth's clouds are. It is more likely composed of hydrocarbon particles, complex organic compounds produced when ultraviolet light from the Sun and charged particles from Neptune's magnetosphere break apart simple molecules like methane and nitrogen in the upper atmosphere, allowing them to recombine into larger, more complex molecules that eventually settle toward the surface as fine particles. This same photochemical process produces the orange haze that gives Saturn's moon Titan its color and creates the complex organic chemistry on Titan's surface that has made it one of the most scientifically interesting objects in the solar system. On Triton, the process operates at a much lower level of activity. The atmosphere is thinner, the available energy is less, but it is occurring. The surface of Triton is being coated over millions of years with the products of atmospheric chemistry driven by solar ultraviolet radiation. Over billions of years, this coating has altered the surface composition and contributed to the pink-orange tint visible in Voyager 2's images. Now, the atmosphere, the geysers, the surface chemistry, all of this exists on a moon that is currently in a stable orbit. Stable, but not permanent. The retrograde orbit that marks Triton as a captured object is not merely an interesting anomaly. It has a consequence that plays out over hundreds of millions of years, and the consequence is irreversible. Tidal forces. When a moon orbits a planet, the planet's gravity creates a slight tidal bulge in the moon, a stretching of the moon's shape toward the planet on the near side and away from it on the far side. The same effect raises ocean tides on Earth as the moon pulls on the oceans. But there is a more subtle tidal interaction as well, one that operates on the orbital energy of the moon itself. When a moon orbits in the same direction the planet rotates, a prograde orbit, The tidal bulge raised in the planet by the moon's gravity is carried slightly ahead of the moon by the planet's rotation. The bulge pulls the moon forward in its orbit, giving it energy, causing the orbit to gradually expand over time. This is what is happening to Earth's moon right now. The moon is spiraling steadily outward, moving about 3.8 centimeters farther from Earth each year. Over billions of years, this has moved the moon from a much closer initial orbit to its current distance. Triton's retrograde orbit reverses this process entirely. Because Triton moves opposite to Neptune's rotation, the tidal bulge raised in Neptune by Triton's gravity is carried in the opposite direction relative to Triton's position. Instead of pulling Triton forward in its orbit, Neptune's tidal bulge pulls Triton backward, removing energy from the orbit, causing the orbit to gradually shrink. Triton is spiraling inward. Measurably, calculably, inevitably, even when imperceptible on a human timescale. Current estimates place the rate of orbital decay at a level that will bring Triton within Neptune's Roche limit, the distance at which tidal forces exceed the self-gravity holding the moon together, in approximately 350 million years. That span exceeds the entire age of the dinosaurs. It is longer than the time since the first dinosaurs appeared on Earth. It is roughly the age of the oldest vertebrate fossils currently known. It is a span of time that reduces any human concern to absolute irrelevance. But it is not infinite. The process is occurring right now, in this moment, as the story continues. Triton's orbit is measurably different from what it was 1 million years ago. It is measurably different from what it will be 1 million years from now. The moon is falling, slowly, silently, in the cold, dark 4.5 billion kilometers from Earth. And it has been falling since the day Neptune caught it. When that boundary is crossed, the inward spiral will continue. The inward spiral will continue, and as the orbit shrinks, the tidal forces will grow. The difference in gravitational pull between the near side and the far side of Triton, the tidal gradient, will increase until it exceeds the internal strength of the rock and ice that holds Triton together. At that point, the moon will begin to break apart. Not explosively, not in an instant, gradually, over millions of years, pieces of Triton will be pulled away from the central mass, following slightly different orbital paths, spreading around Neptune in a ring of debris. The ring will initially be irregular, composed of large fragments, uneven in distribution, creating a structure nothing like the smooth, geometrically regular rings of Saturn. But over millions of additional years, collisions between fragments will break the large pieces into smaller ones, and smaller ones into smaller ones still, and the distribution will gradually even out into something that, seen from a distance, might resemble the ring systems of the outer solar system. Neptune already has rings. 5 of them, formally named Gali, Leverrier, Lassell, Arago, and Adams. They were first detected by Earth-based observations in the 1980s, when the rings briefly blocked the light of a star passing behind Neptune, a technique called stellar occultation. Voyager 2 confirmed their existence and provided detailed measurements. The Adams ring is the most prominent. It contains several denser regions called ring arcs, sections of the ring where material is significantly more concentrated than in the rest of the ring. These arcs are named Liberté, Égalité, Fraternité, and Courage. The existence of stable ring arcs is puzzling. Ring arcs should not be stable. The collisions between particles in a ring and the differential orbital velocities of particles at slightly different distances from the planet should spread material evenly around the orbit over timescales of decades to centuries. Yet the atom's ring arcs have persisted for as long as they have been observed. The leading explanation involves gravitational resonances with Galatea, a small moon that orbits just inside the atom's ring. Galatea's gravity creates a resonance pattern that confines material to certain arcs of the orbit, preventing it from spreading. The moon acts as a shepherd, herding ring particles into clumps and keeping them there. But the atom's ring arcs are not perfectly stable. Observations made from the Hubble Space Telescope and ground-based observatories over the years following the Voyager 2 flyby showed that the arcs had changed. Some had faded. Some had shifted slightly in position. The shepherding mechanism, whatever its precise nature, is not perfectly efficient. The rings of Neptune are dynamic. They evolve. They are, in a sense, alive in the way that any complex physical system with ongoing inputs and dissipative processes is alive, changing continuously, never in exactly the same configuration twice. When Triton eventually disintegrates, the material it contributes will be far more substantial than anything currently in Neptune's ring system. Triton's mass, equivalent to about half the mass of Earth's moon, spread into a ring, would create a structure that dwarfs the current rings in both mass and extent. Neptune would become, in the distant future, a ringed planet in the way Saturn is ringed today. The irony is complete. Triton was likely captured from the Kuiper Belt, the vast reservoir of ice and rock that extends beyond Neptune's orbit and contains hundreds of thousands of objects, ranging in size from small fragments to dwarf planets the size of Pluto. It survived the violence of its capture. It has orbited Neptune for billions of years, and its final contribution to the planet that caught it will be a ring system that may persist for billions of years after the last trace of Triton as a coherent world has disappeared. What was captured will become decoration. What was a world will become a ring. The Kuiper Belt from which Triton likely came is a place that planetary science has only recently begun to understand in detail. It begins roughly at Neptune's orbit, at about 30 astronomical units from the Sun, and extends outward to perhaps 50 astronomical units, though its outer edge is not sharply defined. Within this region, hundreds of thousands of objects orbit the Sun in a broad, flattened distribution that occupies a band centered roughly on the plane of the solar system. Pluto is the best-known Kuiper Belt object. Its orbit takes it from roughly 30 to nearly 50 astronomical units from the Sun, well within the Kuiper Belt's range. Its surface of nitrogen ice, methane ice, and complex organic compounds, its thin nitrogen atmosphere, and its system of moons, including the large companion Charon. All of these characteristics are consistent with formation in the cold outer solar system, in the same environment that produced Triton. The similarity between Pluto and Triton is not coincidental. They formed in the same place, under the same conditions, from the same materials. They are cousins, members of the same population of cold, icy bodies that condensed in the outer reaches of the protoplanetary disk when the solar system was young. Triton was captured, Pluto was not. That single difference, capture versus escape, determined the ultimate fate of two otherwise similar worlds. Pluto remains in its independent orbit, cold and distant and stable, scheduled to continue orbiting the Sun for billions of years into the future. Triton is falling. The captured moon's story will end in destruction. The free world story will continue until the sun itself changes. Two similar objects, two profoundly different futures, decided by a single encounter 4 billion years ago in the chaos of the early solar system. The universe does not choose, it simply follows the equations. Neptune's Great Dark Spot, observed by Voyager 2 in 1989, was a storm system roughly the size of Earth, an oval of darker blue atmospheric material embedded in the lighter blue of the surrounding cloud deck, rotating counterclockwise with a period of approximately 16 days. By analogy with Jupiter's Great Red Spot, the centuries-old storm that has persisted as a visible feature since at least the 17th century, the Great Dark Spot appeared to be a long-lived, stable atmospheric structure. It was not. When the Hubble Space Telescope turned toward Neptune in 1994, just 5 years after Voyager 2's visit, the Great Dark Spot was gone. Not diminished, not faded, gone. The location where it had existed showed nothing, the same uniform blue of the surrounding atmosphere, with no indication that a storm the size of Earth had occupied that position 5 years earlier. A new dark spot had appeared in the northern hemisphere, in a location and with a structure different from the original. This was extraordinary. Jupiter's Great Red Spot has persisted for at least 350 years of continuous observation. The assumption had been that large storm systems on giant planets were stable, long-lived features, maintained by the same deep atmospheric circulation patterns that create and sustain them. Neptune's atmosphere operates differently. The storms that form and dissipate in Neptune's atmosphere appear to do so on timescales of years to decades, far shorter than the centuries-long persistence of Jovian storms. The Great Dark Spot that Voyager 2 observed was perhaps only a few years old when the spacecraft arrived, and it disappeared within a decade. The atmospheric dynamics that drive Neptune's winds, storms, and large-scale weather patterns are not well understood, in large part because only one spacecraft has ever been there for only a few hours, and Earth-based observations lack the resolution to track fine-scale atmospheric features in detail. What is known is that Neptune's atmosphere is far more variable and dynamically active than any other planet in the outer solar system, despite receiving far less solar energy than any of them. The extreme winds, the disappearing storms, the internal heat that may compress carbon into diamond deep in the mantle. Neptune is a planet full of surprises, and most of its surprises remain unexplained. The data from Voyager 2 represents the baseline, a single snapshot of a complex evolving system taken at one moment in time from one trajectory with instruments designed in the 1970s. Everything that has been learned about Neptune since 1989 has come from telescopes. Earth-based observatories have tracked the ring arcs, measured atmospheric changes, discovered new moons. The Hubble Space Telescope has returned periodic images of Neptune's disk, revealing the appearance and disappearance of storm systems, tracking changes in atmospheric banding, measuring shifts in color and brightness. But telescopes, however powerful, cannot do what a spacecraft can do. They cannot enter the atmosphere. They cannot measure the magnetic field from close range. They cannot fly through the ring system and count the particles. They cannot photograph the surface of Triton in detail. Voyager 2's best images of Triton covered less than half the moon's surface, and at a resolution that left most geological features unresolved. There is a hemisphere of Triton that no instrument has ever seen. Not blurry, not partially resolved, simply unseen, never photographed, never measured, never examined in any way. It was in shadow during Voyager 2's flyby, or facing away from the spacecraft, or simply never in the field of view of any instrument that has operated since 1989. Half of a world, unseen. The proposals for future missions to Neptune and Triton have been developed by planetary scientists for decades. The scientific case is compelling. The discoveries that await a dedicated orbiter, or better, an orbiter combined with a Triton lander or atmospheric probe, are considered among the highest priority targets in planetary science. And yet, as of now, no mission is funded. No spacecraft is being built. No launch date is set. The next time a human-made object will observe Neptune up close depends on decisions that have not yet been made, budgets that have not yet been approved, and engineering work that has not yet begun. That August marked the beginning of a long gap. Neptune and Triton are out there. The geysers are firing, the winds are blowing, the orbit is decaying. The rings are shifting. The unseen hemisphere of Triton is rotating slowly in the dark, facing a direction from which no observer has ever looked. And the solar system's most distant large planet remains, after nearly 40 years, the least explored world that Voyager 2 visited. 4 planets in 12 years. 1 flyby for each. And only for Neptune, only at the end of the journey, at the last planet, at the outermost place in the system, was there never a follow-up. Only Neptune was left without a follow-up. The reasons are not mysterious. They are practical, financial, and in their own way sobering. A mission to Neptune takes time that missions to Mars or Jupiter do not require. Even with optimal launch windows and advanced propulsion, technologies that exist today but require development and validation, travel time to Neptune measures in decades, not years. The instruments that launch aboard such a spacecraft must be designed to survive that journey and remain functional upon arrival. The scientists who propose the mission may be approaching retirement by the time it returns data. The students who study planetary science in anticipation of the mission's results will have careers defined by a mission planned before they began their training. The investment is long. The return is distant in every sense of the word. And yet the case for going back has never been stronger. The discovery in recent decades that ice giants like Neptune and Uranus may be the most common type of planet in the galaxy, more abundant than gas giants like Jupiter, perhaps even more abundant than rocky planets like Earth, gives Neptune an importance beyond its status as the 8th planet in this system. Understanding how Neptune formed, how its atmosphere circulates, how its magnetic field is generated, how Triton was captured, and how it is evolving. These questions are not only about Neptune. They are about every ice giant in every planetary system, orbiting every other star. They are about the category of world that may, statistically, be the most representative planet type in the universe. Neptune is not just the end of this solar system. It may be the beginning of understanding the most common kind of world that exists. And Triton, with its captured origin, its active geysers, its slowly decaying orbit, is a laboratory for processes that occur throughout the solar system and beyond. Captured moons exist around other planets, retrograde orbits occur. Tidal dissipation reshapes worlds. Understanding how these processes unfold in detail with a spacecraft that can measure and image and sample would extend knowledge far beyond this single moon. The science waits. The planet waits. The moon waits, orbiting in the wrong direction, erupting in the cold, falling in slow motion toward a fate it cannot alter. And somewhere in the files and proposals and mission concepts of planetary science institutes and space agencies, the plans for returning wait as well, written, revised, presented, deferred, and written again, waiting for the moment when the long journey back to the outermost place finally begins. The early solar system was not the orderly arrangement of planets that exist today. 4.5 billion years ago, the sun had just ignited. Around it, a disk of gas and dust, the remnant of the collapsing cloud of material from which the sun itself had formed, was slowly consolidating. Dust grains collided and stuck together. Pebbles formed, rocks formed, planetesimals, bodies ranging from kilometers to hundreds of kilometers across, formed and began colliding with each other in turn, some breaking apart, others merging and growing. The process of planet formation was violent, chaotic and slow by human standards, but extraordinarily rapid by geological standards. Within the first 100 million years of the solar system's existence, the 4 inner rocky planets had largely assembled. Jupiter and Saturn had formed and grown massive enough to begin influencing the orbits of everything else. And the outer solar system was in flux. The current positions of the outer planets are not where they formed. The leading model of outer solar system evolution, developed in the early 2000s by a group of planetary scientists working in Nice, France, and consequently called the Nice model, proposes that Jupiter, Saturn, Uranus, and Neptune formed much closer to the Sun than they currently orbit, and that gravitational interactions between the giant planets caused them to migrate outward over hundreds of millions of years. In the Nice model, Neptune originally formed inside what is now Uranus's orbit. The 2 planets switched positions, Uranus migrating outward while Neptune migrated even further, crossing through the outer disk of planetesimals, scattering them in all directions. Some were flung inward toward the inner solar system, a period of intense bombardment that may explain the high crater densities visible on the Moon, Mars, and Mercury. Others were scattered outward into the distant orbits that define the Kuiper Belt and the Oort cloud today. During this period of migration and scattering, the region beyond Neptune was populated with icy bodies, objects that had formed in the cold outer disk, rich in water ice, methane ice, nitrogen ice, and complex organic compounds. Pluto was one such object. Eris was another. And somewhere in that population, orbiting peacefully in a trajectory it had maintained since formation, was a body roughly 2,700 kilometers across. The body that would become Triton. The sequence of events that led to Triton's capture is not directly observable. No instrument recorded it. No data exists from that moment. What is known comes from orbital mechanics, from working backward through the equations to determine what initial conditions could have produced the orbit that Triton occupies today. For Triton to have been captured into a stable orbit around Neptune, the capture had to remove energy from Triton's trajectory. An object passing near a planet on a hyperbolic trajectory, a trajectory with enough energy to escape, will simply swing around the planet and continue on its way. This is a gravitational assist, the same maneuver that Voyager 2 used to gain speed at Jupiter, Saturn, and Uranus. The planet deflects the object's path but does not retain it. For capture to occur, the incoming object must lose energy. One mechanism is collision with an existing moon. If Triton, during its passage through Neptune's gravitational sphere of influence, collided with or passed very close to a moon already orbiting Neptune, the interaction could have transferred enough energy to reduce Triton's speed below escape velocity. Triton would remain. The existing moon would be disrupted, likely ejected from the system or broken apart. This scenario predicts that Neptune once had a different moon system, prograde moons that formed alongside the planet, and that most or all of that original system was destroyed when Triton arrived. The current moon system of Neptune is consistent with this prediction. The small, irregular inner moons, Naiad, Thalassa, Despina, Galatea, Larissa, Proteus, have orbital properties that suggest they are not original members of Neptune's system. They may be fragments of a larger moon that was disrupted when Triton arrived, or they may have coalesced from debris left behind by the disruption. A second capture mechanism involves a binary system. Triton, rather than arriving alone, may have arrived as part of a gravitationally bound pair, two similarly sized Kuiper Belt objects orbiting each other as they moved through the outer solar system. When this binary system passed close to Neptune, the tidal difference in Neptune's gravity across the pair could have separated them. One object, the one that became Triton, would have been captured. The other would have been ejected, sent off on a different trajectory, perhaps to become a distant irregular moon of another planet, or perhaps to leave the solar system entirely. This binary capture mechanism has gained support in recent years because it requires no collisional disruption of an existing moon system and is consistent with the frequency of binary objects in the Kuiper Belt. A significant fraction of Kuiper Belt objects are binaries, pairs of similarly sized objects in mutual orbit. If binary capture is the correct explanation for Triton, it means that the same type of event could have occurred at other planets as well. Two worlds traveling together, one caught, one lost. The capture, however it occurred, was not the end of the violence. When Triton first entered Neptune's gravitational sphere of influence, its orbit was highly eccentric, a long elliptical path that brought it close to Neptune at one end and carried it far away at the other. The initial orbit may have been so eccentric that Triton's closest approach to Neptune brought it inside the current orbits of Neptune's inner moons. An eccentric orbit in the presence of tidal forces is not stable. Each time Triton passed close to Neptune, Neptune's gravity raised tidal bulges in Triton's interior, flexing and straining the rock and ice. This tidal deformation dissipated energy as heat. The heat came from the orbital energy of Triton itself, energy removed from the orbit and deposited into Triton's interior as warmth. The orbit shrank, the eccentricity decreased. With each close approach, Triton's orbit became slightly more circular and slightly smaller. This process of tidal circularization took time. Estimates range from tens of millions to hundreds of millions of years, but it operated continuously, driven by the same physics that drives tidal heating on Io today. The result was a gradual transition from an eccentric, chaotic capture orbit to the nearly circular retrograde orbit that Triton currently occupies, at a distance of approximately 354,000 kilometers from Neptune's center. During the period of tidal circularization, Triton was warm. The energy deposited by tidal flexing may have been sufficient to maintain a subsurface ocean of liquid water, perhaps for hundreds of millions of years after capture. If this is the case, Triton once had an interior ocean, heated not by radioactive decay or solar radiation, but by the mechanical energy of its own orbital adjustment. Whether that ocean persists today is unknown. Triton's density, approximately 2 grams per cubic centimeter, is consistent with a composition of roughly 30 to 45% rock and the remainder water ice and other volatiles. The rock component is dense enough to have sunk toward the center through a process called differentiation, forming a rocky core surrounded by a mantle of water ice. If the tidal heating during orbital circularization was sufficient to maintain a liquid water layer between the rocky core and the outer ice shell, and if enough radiogenic heat is still being generated by radioactive elements in the rock to maintain some warmth today, Triton might still harbor a subsurface ocean. This is speculative. The evidence is indirect. Triton's density, its composition, the theoretical heat budget during tidal circularization. No instrument has measured Triton's interior directly. No seismometer has recorded moonquakes. No radar has penetrated the ice to map what lies beneath. But the possibility is real enough to take seriously. If Triton has a subsurface ocean, even a thin one, even partially frozen, even intermittently liquid, it joins a growing list of outer solar system bodies where liquid water may exist in the present day: Europa, Enceladus, Ganymede, Titan, potentially Pluto, and now Triton. The outer solar system, once assumed to be a collection of frozen, dead worlds, too cold for any chemistry of interest, has revealed itself to be a place where liquid water is not rare. It may be common. The conditions that make liquid water possible, internal heat from tidal forcing or radioactive decay, combined with the insulating effect of an ice shell that traps the heat, are conditions that exist throughout the outer solar system. Life as it is understood on Earth requires liquid water as a medium. It requires chemical energy sources. It requires organic molecules. Triton, during the period of active tidal heating following its capture, had all three. Whether anything arose in that ancient ocean is a question without an answer. The ocean, if it existed, would have been geologically brief, hundreds of millions of years, which sounds long but represents only a fraction of the solar system's age, and a fraction that ended billions of years ago. The conditions that might have supported life on early Triton no longer exist on its surface, but they may exist in some attenuated form in an interior that has never been directly examined. The surface that Voyager 2 photographed in 1989 tells part of the story of Triton's interior history. The cantaloupe terrain, that distinctive pattern of rounded depressions separated by ridges, covering large regions of Triton's surface in a texture unlike anything else in the solar system, is concentrated in the hemisphere that faces away from Neptune. Its origin, as noted, likely involves diaperism, the upward movement of warmer, less dense material through a denser outer layer. For diaperism to produce the surface features visible in Voyager 2's images, Triton's interior must have been warm enough at some point after the surface formed to drive convective movement through the ice. The timing is consistent with the period of tidal circularization, the same period during which an internal ocean may have existed. The cantaloupe terrain may be the surface expression of a warmer interior, now frozen in place, preserving in its form the memory of a time when Triton was geologically active in ways that its current extreme cold no longer permits. The walled plains and smooth volcanic deposits visible in other regions of Triton's surface, regions that appear younger than the cantaloupe terrain based on their relative smoothness and lower crater density, suggest that Triton underwent a period of cryovolcanic activity. Cryovolcanism is the eruption of volatile materials, water, ammonia, nitrogen, methane, in the same way that silicate rock erupts from conventional volcanoes. On a world like Triton composed largely of ices, the equivalent of lava is a mixture of liquid water and dissolved ammonia, which has a melting point significantly lower than pure water and can remain liquid at temperatures well below 0 Celsius. Flows of this material across Triton's surface would create smooth, bright deposits, and exactly such deposits are visible in Voyager 2's images, covering portions of Triton's surface that were probably once rougher or more heavily cratered. Triton was active, perhaps still is, in the cryovolcanic sense. The geysers firing from the southern polar cap are direct evidence that surface processes driven by sublimation are ongoing, whether deeper processes, cryovolcanic flows, diapirism, subsurface liquid movement, are also currently active is a question that only a future spacecraft could answer. The hemisphere of Triton that Voyager 2 did not image contains, somewhere within it, the answers to questions that the partial coverage of 1989 raised without resolving. Is there cryovolcanism in the northern hemisphere? Is the cantaloupe terrain present globally or confined to the southern regions? Are there geysers in the north, active during northern summer, a season that will not arrive until approximately 2065, when northern summer on Triton begins? None of these questions has an answer. The spacecraft that could answer them has not been built. The mission that would carry it has not been funded. And Triton continues its slow orbit around Neptune, rotating once every 5.9 days, the same period as its orbital revolution, locked in synchronous rotation so that the same face always points toward Neptune. The hemisphere that faces Neptune has been mapped. The hemisphere that faces away, the anti-Neptune hemisphere, was partially imaged by Voyager 2. The poles rotate in and out of view on a decades-long cycle tied to Neptune's orbit around the Sun. The southern polar cap, active with geysers in 1989, is slowly moving into shadow as Neptune continues its orbital journey. The nitrogen that sublimated into the atmosphere during southern summer is beginning to refreeze on the surface of the northern hemisphere. In geological time, this is an eye blink. In human time, it is the work of generations. Triton's seasons are long, and its time, measured in the currency of orbital decay, is running. Not quickly, not in any way that creates urgency on a human timescale. But the equations do not pause, and the orbit does not stop shrinking, and somewhere in the 4.5 billion kilometers of cold space between here and there, a moon is moving in the wrong direction, falling almost imperceptibly toward its eventual dissolution into the ring system of the planet that caught it. The next question is not whether this will happen. The next question is what Triton looked like before it arrived here, what kind of world it was in the Kuiper Belt, in the cold outer dark, before Neptune reached out and changed everything. The Kuiper Belt is not empty space punctuated by occasional objects. It is a structured population, a reservoir, a record of the outer solar system's formation that has been preserved in cold and relative isolation for 4.5 billion years. The classical Kuiper Belt, the region between roughly 40 and 50 astronomical units from the Sun, contains objects whose orbits have remained relatively undisturbed since the early solar system. These are called cold classical Kuiper Belt objects, not because of their temperature, which is cold throughout, but because of their orbital dynamics: low inclination, low eccentricity, close to circular, confined near the plane of the solar system. Their orbital calm suggests they formed in place and have not been significantly perturbed since. These cold classical objects have a distinctive physical characteristic: a high binary fraction. A surprisingly large percentage of them, estimated at perhaps 20 to 30%, are binaries, pairs of similarly sized objects orbiting each other in wide, gentle orbits, moving together through the outer solar system as they have for billions of years. The existence of so many binaries in this population tells scientists something important about how Kuiper Belt objects formed. The standard model of planetary formation, in which objects grow by sequential collisions, struggles to explain how so many wide, gentle binaries could have formed and survived. Violent collisions tend to disrupt rather than create such pairs. An alternative formation mechanism called streaming instability proposes that local concentrations of solid particles in the protoplanetary disk can collapse gravitationally on relatively short timescales to form pairs of objects directly without requiring a sequence of collisions. This mechanism naturally produces binaries, and the binary fraction of cold classical Kuiper Belt objects is one of the strongest observational arguments in its favor. If Triton arrived at Neptune as a binary, one member of a pair formed together with a companion in the cold outer disk, both objects would have been products of streaming instability. They would have orbited each other gently for billions of years, moving through the outer solar system in a slow, paired dance. And then Neptune's gravity would have ended it. The separation of a binary during a close planetary encounter is a gravitational exchange. Neptune's tidal forces, the difference in gravitational pull between the two members of the binary, which are at slightly different distances from Neptune, would have pulled the pair apart. One member loses energy in the interaction and is captured. The other gains exactly that energy and is released, ejected on a hyperbolic trajectory. The mathematics of this exchange is precise and conserved. The total energy of the two-body system before and after the encounter is identical. Energy is neither created nor destroyed, it is transferred. Triton received Neptune's capture at the cost of its companion's freedom. Where Triton's companion went is unknown. It may have been ejected into a very distant orbit around the Sun, one of the scattered disk objects that populate the distant outer solar system with highly eccentric, high-inclination orbits. It may have been sent on a trajectory that eventually took it out of the solar system entirely. It may, in the chaos of the early solar system, have encountered other planets, been perturbed again, and eventually settled into some orbit that bears no obvious relationship to its origin. It is out there somewhere, or it was, before some encounter disrupted it further. A world that was once paired with Triton. A world that, by the accident of which side of the binary Neptune's gravity caught, lives in freedom while Triton falls. The Kuiper belt from which both came contains hundreds of thousands of objects larger than 100 kilometers in diameter, and an estimated 100,000 objects larger than 500 kilometers. Most will never be visited by any spacecraft. Most will never be named. Most will orbit the Sun for the remaining lifetime of the solar system, 5 or 6 billion years, in the same cold trajectories they have followed since formation, undisturbed and unexamined. Pluto, the largest known Kuiper belt object until the discovery of Eris in 2005, was visited by the New Horizons spacecraft in July 2015. The images returned by New Horizons revealed a world of unexpected complexity: nitrogen geysers flowing across plains, mountains of water ice rising 3,000 meters above the surrounding terrain, a thin nitrogen atmosphere with haze layers, evidence of geological activity driven by processes not yet fully understood. Pluto, at 39 astronomical units from the Sun, receiving even less solar energy than Neptune, was alive in a way that no one had anticipated. If Pluto is that complex, that geologically active, that chemically diverse, that dynamic, then Triton, which formed in the same environment, under the same conditions, from the same materials, was likely equally complex before its capture. Voyager 2's images of Triton, limited as they are, suggest exactly this: a world of sculpted terrain, cryovolcanic deposits, active geysers, and a differentiated interior that records billions of years of geological activity. Triton is not a simple, uniform ball of ice. It is a world with a history, with internal processes, with a surface that records billions of years of geological and chemical activity. It arrived at Neptune already formed, already complex, already with whatever interior structure and surface chemistry 4.5 billion years of quiet evolution in the outer solar system had produced. And then the capture changed everything. The tidal heating during orbital circularization restructured Triton's interior, melted whatever had been frozen, reshuffled the distribution of heat and chemistry throughout the body. The surface that Voyager 2 photographed in 1989 is not the surface Triton had in the Kuiper belt. It is the surface that emerged after capture, reshaped by the energy of orbital adjustment, modified by billions of years of exposure to Neptune's magnetic environment, coated over billions of years with photochemical products raining down from an atmosphere that Triton barely maintains. Two versions of Triton exist: the one that drifted in the Kuiper belt, pristine and cold, for the first 100 million years of the solar system's existence, and the one that orbits Neptune now, warmed, restructured, slowly falling. The first version is gone. It cannot be recovered or directly studied. The second version orbits right now, at this moment, at a distance of 4.5 billion kilometers from Earth, in the cold dark beyond the last planet. And no one has looked at it closely since August of 1989. The gap between that single visit and now spans more than 3 decades of planetary science. 3 decades during which Cassini orbited Saturn for 13 years. The New Horizons mission revealed Pluto. The Juno spacecraft entered Jupiter's orbit and returned data about its deep atmosphere and magnetic field, and multiple missions explored Mars from orbit and from the surface. The outer solar system has received attention. Neptune has not. The contrast is not a judgment. It is a consequence of distance, cost, and the physics of launch windows, but it is real. And it means that Triton, one of the most scientifically interesting objects in the solar system, a captured world with active geysers and a possibly ocean-bearing interior and a retrograde orbit that encodes the chaotic history of the early solar system, has been examined in detail by exactly one spacecraft for exactly one brief window of time more than 3 decades ago. Everything that is known and everything that is unknown rests on that foundation. The science of Triton is a science of inference, of working from incomplete data from orbital mechanics and theoretical models and the comparison with similar bodies elsewhere to build a picture of a world that no instrument is currently examining. It is science conducted across the silence of decades and the distance of 4.5 billion kilometers. And the picture it has produced is, despite its incompleteness, one of the most remarkable in planetary science. A world that should not be where it is, a moon that moves in the wrong direction, a surface alive with eruptions in the coldest place measured in the solar system, an interior that may have been liquid, that may still be liquid in some deep and unreachable layer, that preserves in its structure the memory of a violent capture billions of years ago. A world falling, slowly, toward a dissolution that the mathematics has already scheduled. Triton is not finished. Its story did not end in 1989, when Voyager 2's cameras looked away and the spacecraft continued into interstellar space. The story continues in the dark and the cold, 4.5 billion kilometers from the nearest human eyes. And it continues now. On August 25th, 1989, the Voyager 2 spacecraft made its closest approach to Neptune. It had been traveling for more than 12 years since leaving Earth. In that time, it had flown past Jupiter in 1979, Saturn in 1981, and Uranus in 1986. Each flyby used the planet's gravity to accelerate the spacecraft and redirect its trajectory, a sequence of precisely calculated maneuvers called the Grand Tour, made possible by a rare alignment of the outer planets that occurs only once every 175 years. The alignment that made the Grand Tour possible in the late 1970s will not occur again until the year 2153. Voyager 2 used it. At closest approach, Voyager 2 passed within 4,950 kilometers of Neptune's cloud tops, closer than any previous spacecraft had approached a giant planet. At that distance, traveling at approximately 15.4 kilometers per second relative to Neptune, the spacecraft's instruments had a narrow window to measure, image, and record as much as possible. The flyby of Neptune lasted hours. The flyby of Triton lasted less time than that, a brief, precise pass at a distance of approximately 40,000 kilometers from Triton's surface, a distance close enough to resolve surface features, but far enough that the images captured only the hemisphere facing the spacecraft at the time of closest approach. In that narrow window, planetary science changed. Before Voyager 2 arrived, Neptune was a featureless blue disk in the best telescopic images available. Triton was a point of light with a measurable spectrum, but no resolved surface features. Everything known about both bodies was indirect, inferred from spectroscopy, from orbital calculations, from theoretical models built on the assumption that the outer solar system behaved in predictable ways. What Voyager 2 found was not predictable. The geysers were the discovery that most surprised the scientists monitoring the incoming data. Active geological features had been detected on other worlds, most dramatically on Io, where Voyager 1 had discovered active sulfur dioxide volcanoes in 1979. But Io orbits Jupiter and is heated to extreme temperatures by the tidal forces of the solar system's most massive planet. Io's volcanism is violent, continuous, and energetically understandable given the immense tidal forces it experiences. Triton orbits Neptune, a planet with 1/17 of Jupiter's mass, at a distance of approximately 354,000 kilometers. The tidal heating available to Triton in its current, nearly circular orbit is minimal. Surface temperatures at -235 degrees Celsius are the coldest measured anywhere in the solar system. Nothing about these conditions suggested active surface processes. And yet, the images of Triton's southern polar region showed dark streaks running downwind for distances of up to 150 kilometers. The streaks were consistent in orientation, all aligned in the same direction, indicating a prevailing wind direction in Triton's thin atmosphere. In several images captured what appeared to be active plumes, dark columns rising from the surface and then bending downwind before dispersing. The team analyzing the images took time to be certain. Active eruptions on the coldest surface in the solar system, driven by sunlight too faint to warm the surface appreciably. This was not a result that could be announced casually. The data were examined, the alternative explanations were considered and ruled out, and the conclusion was confirmed. Triton had geysers. The mechanism, worked out in detail in the years following the Voyager 2 flyby, is the solid-state greenhouse effect described earlier, transparent nitrogen ice, allowing sunlight to penetrate and warm a dark substrate below, building pressure until the overlying ice is breached, and nitrogen gas erupts through the opening, carrying dark material upward. But the details of the mechanism, studied closely, reveal layers of complexity that the simple description does not capture. The dark material carried upward by the geysers is not simply a passive tracer. It is likely a mixture of complex organic compounds, tholins, produced by the irradiation of simple molecules like methane and nitrogen by ultraviolet light from the sun and charged particles from Neptune's magnetosphere. These compounds accumulate on the surface over time, building up a dark, chemically complex layer that both enables the geysers by absorbing sunlight and records in its chemistry billions of years of interaction between Triton's surface and the radiation environment around Neptune. Tholins are the same class of compounds found on Titan, on Pluto, on comets, and in interstellar space. They are the products of radiation chemistry operating on simple carbon and nitrogen compounds, the raw material of organic chemistry, the chemical precursors from which, under the right conditions, amino acids and nucleobases can form. On Triton, tholins are present on the surface and are being continuously produced. Their chemistry is not life, but it is the chemistry that, on Earth, preceded life, the chemistry of the early atmosphere and ocean, in which the molecular building blocks of biology were first assembled. The surface of Triton is a laboratory for prebiotic chemistry, operating in the cold dark at the edge of the solar system. The geysers, by carrying surface material upward into the atmosphere and depositing it downwind, are continuously redistributing this chemical material across the surface. They are mixing the chemistry, spreading the dark organic deposits, creating new configurations of material in new locations. The streaks left by the geysers are not merely a geological curiosity. They are a record of atmospheric activity, surface chemistry, and the interaction between Triton's interior, where the pressure builds, and its exterior, where the material is released. Each streak is a geological document. The orientation of the streaks tells scientists the direction of the prevailing wind in the southern hemisphere during the period when the geysers were active. The length of the streaks tells them the settling velocity of the ejected particles relative to the wind speed. The darkness of the deposits tells them the concentration and composition of the dark material carried up from the substrate. From the pattern of streaks alone, Voyager 2's scientists were able to reconstruct a picture of atmospheric dynamics on a world they had never visited and could observe for only hours. This is the power of careful measurement. The thin atmosphere through which the geyser material travels is itself a subject of considerable scientific interest. Triton's atmosphere was first detected by stellar occultation, the same technique that confirmed the existence of Neptune's rings. When Triton passes in front of a distant star, as seen from Earth, the star's light dims and brightens in a characteristic way as the atmosphere refracts it. The pattern of brightening and dimming reveals the atmospheric density profile, how the density changes with altitude. From these occultation measurements, made before and after the Voyager 2 flyby, and continuing to the present, the structure of Triton's atmosphere has been mapped with surprising detail for a world so distant. The troposphere extends from the surface to approximately 8 kilometers altitude. Above it, the stratosphere reaches to roughly 30 kilometers. The haze layers detected by Voyager 2, thin layers of hydrocarbon particles suspended in the lower atmosphere, occur within this altitude range. The most striking result from occultation measurements made in the years following the Voyager 2 flyby was unexpected and initially puzzling. Triton's atmosphere was getting thicker. Between 1989 and observations made in the 1990s and 2000s, the atmospheric surface pressure increased by a measurable amount, roughly doubling over the period of observation. This increase is consistent with a warming of Triton's surface, driven by seasonal changes in solar illumination as Neptune progresses in its orbit around the Sun. Triton's southern hemisphere has been in summer for the past several decades. The south polar cap, the bright nitrogen ice deposit that covers the southern polar region, has been receiving maximum solar illumination. Nitrogen has been sublimating from the cap, entering the atmosphere, increasing the atmospheric pressure. As Neptune continues in its orbit and the southern hemisphere moves toward autumn, the situation will reverse. The southern cap will stop sublimating. The northern cap will begin to receive more sunlight. Nitrogen will begin to migrate from south to north, refreezing gradually on the northern cap. The atmospheric pressure will decline again. This cycle, driven by Neptune's 164-year orbit around the Sun, gives Triton a global climate system, a redistribution of volatiles from pole to pole as the seasons change, that operates on timescales longer than recorded human history. The current southern summer will not end for decades. Northern summer will not arrive until approximately 2065. When it does, the geysers in the northern hemisphere, if they exist, as the symmetry of the mechanism suggests they should, will become active for the first time since any instrument was present to observe them. No instrument will be present in 2065 unless a mission is launched soon. The round-trip travel time to Neptune is measured in decades. A spacecraft launched in the late 2020s or early 2030s with current propulsion technology would arrive in the 2040s at the earliest. It could potentially be in orbit around Neptune in time to observe the onset of Triton's northern summer, to watch the polar cap shift, the geysers activate, the atmosphere change. This convergence of opportunity has been noted by planetary scientists for years. The mission that could observe these seasonal changes, the Neptune Odyssey concept studied by NASA, or the Trident mission concept proposed for the Discovery program, would arrive at exactly the right moment in Triton's seasonal cycle to witness the northern hemisphere emerging from decades of winter. The timing is not infinite. The window is constrained. Every year that passes without a launch narrows the window. The season is turning. The instruments that could watch it have not yet been built. Beyond the geysers in the atmosphere, the surface of Triton, recorded in Voyager 2's images, preserves a history of geological processes spanning billions of years. The cratering record is sparse by the standards of the inner solar system. The moon's surface is saturated with craters accumulated over 4 billion years. Mars is heavily cratered. Mercury is heavily cratered. These surfaces have been stable for billions of years, and every impact has left a permanent record. Triton's surface has relatively few craters. This could mean several things. It could mean that Triton has been geologically active, that surface processes have resurfaced large areas, erasing the impact record. The cryovolcanic deposits, the cantaloupe terrain, the smooth plains visible in Voyager 2's images, all suggest active resurfacing at various points in Triton's history. It could also mean that Triton, during its period as a free-ranging Kuiper Belt object before its capture, accumulated fewer craters than the inner solar system bodies, because the Kuiper Belt, while populous, is less densely packed with impactors than the region between Mars and Jupiter was during the period of heavy bombardment. Or it could mean both, a low initial crater flux combined with active resurfacing that erased many of the impacts that did occur. Distinguishing between these possibilities requires dating the geological features, determining which are older and which are younger, establishing a timeline of surface evolution. On the Moon and Mars, this has been done by comparing crater densities with radiometric ages of returned samples. More craters means older terrain. Fewer craters means younger terrain. On Triton, no samples have been returned. No radiometric ages exist. The crater density must be interpreted using models of impactor flux in the outer solar system, models that are themselves uncertain. The geology of Triton is therefore interpreted in relative terms. This terrain appears older than that terrain, based on crater density and the degree of modification of surface features. This unit appears to overlie that one, suggesting it formed later. This smooth deposit appears to have flowed across and partially buried older, rougher terrain. From these relative relationships, a sequence of geological events can be proposed, but not dated in absolute terms. What the sequence suggests is a world that was active early in its history, experienced a period of intense resurfacing after its capture by Neptune when tidal heating was most intense, and has since cooled to a state of lower activity, with the geysers representing the most energetic ongoing surface process. The walled plains, smooth, bright, roughly circular features that may represent ancient impact basins, partially flooded by cryovolcanic material, are among the oldest identifiable features on Triton's surface. They suggest a period early in Triton's history around Neptune, when the interior was warm enough and fluid enough to produce substantial cryovolcanic eruptions that reshaped the surface. The cantaloupe terrain is likely younger than the walled plains, produced by diapurism operating over the long period of slow cooling following the intense tidal heating of orbital circularization. The smooth nitrogen and methane frost deposits of the polar caps are the youngest features, deposited and redistributed seasonally, continuously refreshed by the cycle of sublimation and condensation that follows Neptune's orbit around the Sun. Triton's surface is a layered record. At the bottom, ancient rock and water ice, the original material of a Kuiper Belt world. In the middle, the modifications of capture, cryovolcanic deposits, tidal fractures, the diapyrically sculpted cantaloupe terrain. At the top, seasonal frost, geyser deposits, photochemical residues accumulating year by year in the cold sunlight 4.5 billion kilometers from Earth. Each layer represents a different chapter in a history that spans the full age of the solar system. The chapter that is currently being written in the dark and the cold involves falling. Not fast, not visible, not measurable on a human timescale, but in the equations that describe the interaction of tidal forces and orbital mechanics, the chapter is clear. Triton is approaching Neptune. The approach is measured in millimeters per year, a number so small it defies intuitive grasp, but a number that accumulates over millions of years into a significant change in orbital radius. The orbit that Triton occupies today is measurably smaller than the orbit it occupied when Voyager 2 flew past in 1989. The difference is unmeasurable by any instrument currently in operation, too small, over 35 years, to detect against the background noise of measurement uncertainty. But the mathematics says it is smaller. It will continue to be smaller. And eventually, not soon, not in any time frame that humans will experience, the orbit will have shrunk to the point where tidal forces dominate over the self-gravity of Triton's rock and ice, and a world will begin to come apart. The material of Triton, the nitrogen ice, the water ice, the rock, the organic compounds accumulated over billions of years, will spread into a ring. The ring will circle Neptune at the orbital distance where tidal forces ultimately prevail. And Neptune will have gained a ring, and the solar system will have lost a world. The conversion is irreversible. No force will reassemble the ring material into a moon. No process will reconstitute the complex geological structure, the layered history, the interior ocean, the geyser vents, the sculpted surface, from a dispersed ring of debris. What took 4.5 billion years to build will take a few 100 million years to destroy. The physics does not mourn, but the knowledge of it, held in the minds of the scientists who have studied Triton's orbit, calculated the decay rate, worked through the implications, carries something that the physics does not. An awareness of what is being lost. Not soon, not urgently, not in any time frame that demands immediate response. But the awareness that this world, complex, active, carrying within it a history that extends to the origin of the solar system, is impermanent. That its time, though vast by human standards, is finite. That in the long run of the solar system's future, Triton's existence as a coherent world is an episode. The episode continues, and somewhere in the cold that surrounds Neptune, the geysers continue to fire, nitrogen erupting into a near vacuum, dark material spreading downwind across the bright polar cap, the same process that was occurring when Voyager 2's camera captured it in 1989, the same process that will continue until the last nitrogen ice sublimates from the last warm spot and the last geyser falls silent. The silence, when it comes, will be the silence of a world that is no longer whole. But that silence is geologically distant, measured in hundreds of millions of years. For now, the geysers fire. The orbit holds. In the story of what happens next, to the orbit, to the ring system, to Neptune's future appearance in the sky of whatever world might observe it, continues in the slow, enormous timescale of the outer solar system. The Voyager 2 spacecraft, after completing its flyby of Neptune and Triton, did not stop. It could not stop. No propulsion system powerful enough to decelerate from 15 kilometers per second exists on the spacecraft, and even if it did, firing such a system would require fuel that was never loaded, because the mission was not designed to stop. Voyager 2 was designed to fly. It continues to fly now. As of 2026, it is approximately 20 billion kilometers from Earth, well beyond the heliopause, the boundary where the solar wind's influence gives way to the interstellar medium. It is one of 5 spacecraft to have achieved escape velocity from the solar system, joining Voyager 1, Pioneer 10, Pioneer 11, and New Horizons on outbound trajectories that will carry them through interstellar space indefinitely. Its power source, 3 radioisotope thermoelectric generators, fueled by the radioactive decay of plutonium-238, continues to produce electricity, though at a declining rate. Scientific instruments are still operating, returning data about the interstellar environment. The signal that carries that data travels at the speed of light and takes more than 18 hours to reach Earth. Voyager 2 is still talking? What it experienced in those hours of closest approach to Neptune and Triton in August 1989 represents the entirety of direct, close-range measurement of these worlds. Its 10 scientific instruments, the imaging science system, the photopolarimeter, the ultraviolet spectrometer, the infrared interferometer spectrometer and radiometer, the plasma science experiment, the low-energy charged particles detector, the cosmic ray subsystem, the magnetometer, the plasma wave subsystem, and the planetary radio astronomy instrument, each collected data for a few hours as the spacecraft swept through the Neptunian system. The imaging system alone returned more than 9,000 images of Neptune, its rings, and its moons during the encounter. 9,000 images. From a spacecraft that had crossed the entire outer solar system to get there. From a flyby that lasted hours. From a single trajectory that could not be adjusted to revisit anything, could not slow down to examine a feature more closely, could not orbit to study the seasonal changes that planetary scientists would later want to understand. 9,000 images, and then the spacecraft was past the system, and the images stopped and the silence began. The engineers who built Voyager 2 designed it to operate in the hostile environment of deep space for at least 5 years through the Jupiter and Saturn flybys. The spacecraft was 40 years old when it crossed the heliopause. Its systems have outlasted every design requirement by decades. But the cameras, the imaging science system that returned those 9,000 images, were powered down in 1990, the year after the Neptune flyby, to conserve electrical power. The power budget of Voyager 2, already declining as the plutonium decays, was insufficient to maintain all systems simultaneously. Instruments were deactivated one by one as the power supply dropped. The cameras that saw Triton went dark 36 years ago. No image of Triton has been taken since. The infrared measurements that established Triton's surface temperature, the coldest measured anywhere in the solar system, were taken by the infrared interferometer spectrometer during the flyby. This measurement established that Triton's surface was colder than the theoretical equilibrium temperature would predict for a body at Neptune's distance from the Sun. The discrepancy exists because Triton's surface is extremely reflective. The nitrogen ice that covers much of the surface has an albedo, a reflectivity, of approximately 70 to 80%. This means that 70 to 80% of the sunlight that reaches Triton is reflected away rather than absorbed. Only 20 to 30% is absorbed and converted to heat. The high albedo is maintained by the seasonal deposition of fresh nitrogen frost, the same process that is redistributing the polar cap material in response to seasonal changes in solar illumination. Fresh frost is bright. Dark material accumulates on older frost surfaces. The cycle of deposition and sublimation continuously refreshes the bright, high albedo surface. This reflectivity is why Triton is so cold. It reflects away most of the already faint sunlight that reaches it. And it is precisely because the surface reflects so much light that the greenhouse mechanism can function as a geyser driver. The transparent nitrogen ice sitting atop the dark substrate allows the small fraction of sunlight that penetrates it to reach the absorbing material below. The dark substrate, with its lower albedo, absorbs what the bright surface above reflects away. The geometry, dark material covered by transparent ice, creates a situation where absorbed energy is trapped rather than radiated back, building pressure in the only way the physics permits. The geysers are a consequence of the same reflective surface that makes Triton the coldest place measured in the solar system. The cold creates the ice creates the greenhouse drives the geysers. The geysers redistribute the dark material feeds the greenhouse. It is a cycle, a self-sustaining process, operating quietly, continuously, in the cold dark at the edge of everything. The surface chemistry is equally self-sustaining in its own way. Methane on Triton's surface is continuously being irradiated by ultraviolet light from the Sun and by energetic charged particles from Neptune's magnetosphere. The radiation breaks the methane molecules apart, cleaving the carbon-hydrogen bonds, releasing fragments that recombine into larger, more complex molecules. The process is slow but continuous. Over millions of years, simple methane is converted into a complex mixture of organic compounds, the pink-orange tholins that tint Triton's surface and contribute to the dark substrate that enables the geysers. The tholins accumulate, the surface darkens, the geysers spread the dark material. More tholins are irradiated and modified. The chemistry deepens and diversifies. Experiments conducted on Earth using ultraviolet lamps to irradiate mixtures of methane, nitrogen, and other simple molecules at cold temperatures produce tholins whose infrared spectra closely match the spectra of material observed on Triton and Pluto. These laboratory tholins, when exposed to liquid water, spontaneously produce amino acids and other biologically relevant molecules. The implication is not that life exists on Triton. The implication is that the chemistry occurring on Triton's surface, the same chemistry occurring on Pluto, on comets, in interstellar clouds, is the chemistry that, when combined with liquid water and sufficient time, produces the molecular building blocks of life. Triton has the chemistry, it has had liquid water in its past, during the period of tidal heating after capture, it has time, 4.5 billion years of it. Whether those three ingredients were ever combined in the right configuration for long enough under the right conditions is a question that cannot be answered from Earth, from telescopes, or from orbital mechanics. It requires a spacecraft, an instrument, a measurement. The gap of the past 36 years contains, somewhere within it, the answer to whether Triton is simply a fascinating geological object, or something more, a world where the chemistry of life was once assembled, where an ocean once existed, where the conditions for biology were present even as the outer edge of the solar system moved in its long, cold orbit around a distant star. The answer is in the ice, in the dark substrate beneath the transparent frost, in the interior that tidal forces once warmed, and that may, in some deep and unreachable layer, retain a trace of that ancient warmth. It is waiting, and the instruments that could find it, that could measure the interior heat, sample the surface chemistry, image the unseen hemisphere, observe the geysers as they fire, enter orbit, and watch the seasonal changes unfold over years rather than hours, those instruments have not yet been built. The science waits. The world waits. And in the cold dark of the outer solar system, the geysers continue, the orbit shrinks in its unmeasurable increments, and the unseen hemisphere turns slowly through a darkness that no eye has ever examined. The next part of this story belongs to the spacecraft that has not yet left, but the world it will visit is already there. It has been there since the beginning. It will be there recognizably for hundreds of millions of years to come, waiting in the only way a world can wait, by continuing to exist, to change, to follow the physics, and to hold within its ice and rock the record of everything that has happened since the solar system was young. The solar system will not always look the way it does now. Every structure visible in the night sky, every planet, every moon, every ring system is a temporary arrangement. The planets are in orbits that will change. The moons are in relationships with their parent planets that will evolve. The rings of Saturn, spectacular as they are young by geological standards and will fade within 100 million years as ring particles spiral into the planet or escape into space. Everything is in motion, everything is changing. The snapshot that any observer takes of the solar system at any given moment captures a system in transit between what it was and what it will become. Neptune is no exception. The Neptune that exists today, with its 14 moons, its 5 named ring systems, its extreme winds, its lost and reappeared storm systems, is not the Neptune of 4 billion years ago, and it is not the Neptune of 400 million years from now. The most dramatic change scheduled for Neptune's future involves Triton. The orbital decay that is currently reducing Triton's orbital radius by unmeasurable increments per year will, over the course of that vast interval, accumulate into a change of enormous consequence. Triton will cross the gravitational boundary at which tidal forces exceed the self-gravity of a body and begin to break apart. The Roche limit for Triton orbiting Neptune is approximately 12,000 kilometers above Neptune's cloud tops, based on the density of Triton's material and Neptune's gravitational parameters. Currently, Triton orbits at approximately 354,000 kilometers from Neptune's center. The gap between Triton's current orbit and the Roche limit is vast enough that 350 million years of orbital decay are required to close it. But it will close. The initial disruption, when it begins, will be gradual. Tidal forces increase as the distance decreases, because tidal force, the differential gravity across an extended body, scales as the inverse cube of the distance. As Triton spirals inward, the tidal stress increases, gradually at first, then more rapidly as the tidal boundary approaches. The first material to be lost will be loose surface material, frost deposits, fine-grained debris, particles that are not firmly bonded to the bulk of the Moon. These will be stripped from the surface and enter orbit around Neptune, forming the earliest precursors of the eventual ring system. As the orbit continues to decay and the tidal forces grow, larger and larger pieces will be separated from the main body. Fractures will open in Triton's interior. The differentiated structure, rocky core, water ice mantle, outer volatile layers, will be progressively disrupted as the tidal stress overwhelms the material strength of rock and ice. The process from first disruption to complete dispersal will take millions of years. Triton will not simply vanish in an instant. It will come apart piece by piece over a timescale long enough that an observer watching continuously would see the Moon gradually diminish, becoming irregular in shape as large fragments are removed, then progressively smaller as those fragments are themselves broken down by collisions. The fragments will spread along the orbital path, following slightly different trajectories based on their size, density, and the exact conditions of their separation from the main body. Collisions between fragments will further fragment them. The size distribution of the ring particles will shift progressively towards smaller sizes as the collisional cascade proceeds. Eventually, the ring will reach a state where most particles are small enough that sunlight can affect their orbits, where radiation pressure and the Poynting-Robertson effect, which causes small particles to slowly spiral inward as they absorb and re-emit solar radiation, become significant forces. At that stage, the ring will have a finite lifetime, particles spiraling slowly into Neptune's atmosphere, removed from the ring over timescales of millions of years. The ring system created by Triton's disruption will not be permanent, but it will be impressive. Triton's mass is approximately 2.1 times 10 to the 22nd kilograms, roughly 21 billion trillion kilograms. For comparison, the mass of all of Saturn's rings combined is estimated at approximately 1.5 times 10 to the 19th kilograms, more than 1,000 times less massive than Triton. The ring system that Triton's disruption will produce, if the material distributes itself into a ring rather than into a diffuse cloud, will be more massive than Saturn's rings by a factor of roughly 1,000. Whether the resulting ring would be as visually spectacular as Saturn's rings depends on factors that are difficult to predict: the size distribution of the ring particles, their composition and reflectivity, and the exact orbital distribution of the debris. Saturn's rings are spectacular, partly because they contain a large fraction of very reflective water ice particles in a size range that efficiently scatters visible light back toward an observer. Triton's bulk composition, water ice, nitrogen ice, methane ice, rock, and organic compounds, is partially overlapping with Saturn's ring material. The water ice fraction would be reflective. The organic compounds and dark tholins would reduce reflectivity. The eventual appearance of Neptune's future ring system is uncertain. But the scale is not uncertain. Neptune will, in the distant future, be a ringed planet. The ring is already written into the mathematics of the orbit. The inner solar system will be largely unchanged when Triton's disruption begins. 350 million years is long enough for significant evolutionary changes on Earth. The span from the Carboniferous period to the present encompasses the dinosaurs, the extinction events, the entire Cenozoic era, and the emergence of every mammal species alive today. In 350 million years from now, Earth will be recognizably a planet, but nothing about its biology, geography, or even its continental arrangement will be familiar. The sun will be slightly brighter, the Earth-Moon distance will be slightly greater, the continents will have moved, separated, and perhaps rejoined in configurations that no current map anticipates. And in the outer solar system, Triton's disruption will be underway. No human will observe it. No instrument currently operating will be functional. The connection between the physics calculated today and the event that physics predicts is purely mathematical, a line drawn from the present into a future so distant that no continuity of observation or record is possible. The prediction is reliable precisely because it is based on physics that does not change with time. The gravitational constant does not change. The orbital mechanics equations do not change. That calculation depends on material properties and gravitational parameters that are known with sufficient precision. The outcome is not in doubt. Only the timeline carries uncertainty, and that uncertainty is measured in tens of millions of years, not hundreds of millions. The question of what Triton's disruption will mean for the rest of Neptune's moon system is also calculable in outline, if not in detail. The inner moons, Naiad, Thalassa, Despina, Galatea, Larissa, orbit Neptune well inside Triton's current orbit. As Triton spirals inward, it will pass through or near the orbital zones of these small moons. The gravitational interactions during these passages will be complex and potentially disruptive. Some of the inner moons may be ejected from the system. Others may be captured into different orbits. Some may be broken apart by the same tidal forces that are simultaneously destroying Triton. The outcome for the inner moon system depends on the details of the approach trajectory and the masses involved, calculations that become increasingly sensitive to initial conditions as the system's complexity increases. What can be said with confidence is that the Neptune system of 350 million years from now will look fundamentally different from the system that exists today. The dominant moon will be gone. The ring system will be forming or fully formed. The inner moons may be rearranged or absent. Neptune itself will be largely unchanged. The timescales for significant evolution of the planet itself are much longer than the timescale of Triton's disruption. The planet will continue rotating. Its magnetic field will continue operating. Its atmosphere will continue circulating in its extreme patterns. But the sky above Neptune, If sky is a meaningful concept, the cloud tops of a giant planet will be different. Instead of the large, bright disk of Triton moving across the sky in its retrograde arc, there will be a ring spread across the sky in a band, reflecting sunlight at whatever level the ring's particle properties allow, extending from one horizon to the other in the plane of Triton's orbit, which is inclined approximately 23 degrees to Neptune's equatorial plane. A ring inclined to the equatorial plane is unusual. Saturn's rings are close to Saturn's equatorial plane, as are the rings of Uranus. An inclined ring, like the one Neptune will eventually possess, has different dynamical properties. The ring particles experience oscillations perpendicular to the orbital plane, driven by Neptune's gravity, that cause the ring to have a more three-dimensional structure than the flat equatorial rings of Saturn. Over very long timescales, even an inclined ring will flatten toward the equatorial plane as gravitational interactions between ring particles and the planet's oblateness, its slight equatorial bulge, gradually redirect the particles' orbital planes. But on the timescale immediately following Triton's disruption, the ring will be inclined, structured, complex, and enormous. Neptune's distant future as a ringed planet is perhaps the most dramatic of the planetary transformations written into the current solar system's orbital mechanics. Saturn's rings, which have defined its appearance for as long as humans have observed it with telescopes, will be mostly gone in 100 million years. Neptune's rings, which today are faint and barely detectable, will be magnificent in 350 million years. The solar system cycles. The spectacular gives way to the ordinary. The ordinary is transformed, in slow motion, into something new. The deep time of planetary science contains transformations that no human will observe, but that physics has already scheduled, already calculated, already written into the initial conditions of the solar system 4.5 billion years ago. Triton's fate was determined the moment Neptune caught it. Not immediately, not quickly, not in any way that could be detected by watching for a lifetime or a civilization's span of attention, but certainly. The retrograde orbit is the sentence. The tidal mechanics are the grammar. The outcome, the ring, the dispersal, the transformation of a captured world into the decoration of its captor, is the meaning the sentence carries. And somewhere in the cold mathematics of orbital decay, the sentence is being written, one unmeasurable millimeter per year at a time. Now, in this moment, while everything about the human world changes rapidly and unpredictably, the outer solar system is executing a plan that was set before the first cell divided in the first ocean on the young Earth. Before life, before continents, before oceans. The orbit was decaying when the first amino acids assembled in Earth's primordial chemistry. It was decaying when the first fish crossed the boundary from sea to land. It was decaying through the age of dinosaurs, through the asteroid impact that ended them, through every ice age and interglacial, and every civilization that rose and fell in the narrow band of habitable conditions on the third planet from the sun. It is decaying now, and it will continue to decay at the same rate, governed by the same equations, long after everything that currently exists on Earth has been replaced by something else. The outer solar system does not hurry. It does not wait. It simply continues as it always has, following the mathematics with perfect fidelity, toward outcomes that are certain even when they are unimaginably distant. The process is already underway. It has been underway since the day Neptune caught it. The Kuiper Belt beyond Neptune's orbit is also evolving, though on timescales even longer than Triton's orbital decay. Neptune's gravity shapes the Kuiper Belt in ways that are still being mapped and understood. The gravitational resonances between Neptune's orbit and the orbits of Kuiper Belt objects create structured patterns in the distribution of those objects. Pluto is in a 3-to-2 resonance with Neptune. For every 2 orbits Neptune completes, Pluto completes exactly 3. This resonance has protected Pluto from close encounters with Neptune for billions of years, keeping its orbit stable even though it crosses Neptune's orbital path. Thousands of other Kuiper Belt objects are in similar resonances with Neptune. They are called Plutinos, objects locked in the same 3-to-2 resonance as Pluto, or are in other resonances that Neptune's gravity has maintained over billions of years. The existence of these resonant populations is direct evidence of Neptune's outward migration during the early solar system. As Neptune moved outward, it swept resonances through the Kuiper Belt, capturing objects into those resonances as it passed. The current distribution of Kuiper Belt objects, concentrated in resonant populations, depleted in certain orbital regions, structured in ways that reflect Neptune's migration history, is a record of that ancient event, preserved in orbital mechanics, the way a geological layer preserves the chemistry of the environment in which it was deposited. Reading the Kuiper Belt, planetary scientists can reconstruct where Neptune was at different times in its history, how fast it moved, and what it encountered during its migration. The New Horizons spacecraft, after its Pluto flyby in 2015, was redirected to a second target in the Kuiper Belt, a contact binary object called Arrokoth, located at approximately 44 astronomical units from the Sun. Arrokoth was selected in part because its classical Kuiper Belt orbit indicated that it had formed in place and had not been significantly perturbed since formation, making it among the most pristine objects in the solar system. The images of Arrokoth returned by New Horizons in January 2019 showed a remarkable object. 2 lobes joined at a narrow neck, the larger lobe called Wunu and the smaller called Wuyo in the official naming, together nicknamed Mu-69 during the planning phase. The smooth surfaces of both lobes, the absence of significant cratering, and the gentle, low-velocity joining of the 2 components, their shapes fitting together in a way consistent with a slow, gentle merger rather than a high-velocity collision, all supported the streaming instability model of Kuiper Belt object formation. Arrokoth had formed as a binary, the 2 lobes orbiting each other in a gentle dance, and had slowly spiraled together as tidal forces reduced the separation over billions of years. A world built by gravity, slowly, over the age of the solar system. Triton, if the binary capture hypothesis is correct, formed the same way, 2 lobes that merged, or 2 objects that orbited each other and were then separated by Neptune's gravity. The smaller companion, sent away, may resemble Arrokoth in its origin and composition. The larger, caught by Neptune, became Triton. The connection between these objects, Arrokoth drifting undisturbed in the cold outer Kuiper Belt, Triton captured and transformed by Neptune's gravitational embrace, illuminates the range of outcomes available to Kuiper Belt objects. Formation in the same environment, by the same process, can lead to radically different fates depending on a single encounter at a critical moment. The cold classical Kuiper Belt, where Arrokoth resides, is perhaps the most scientifically valuable region in the solar system for understanding planetary formation. It contains objects that have changed the least since formation. It preserves, in the composition and structure and orbital distribution of its members, the conditions that prevailed in the outer solar system 4.5 billion years ago. No mission is currently planned to visit a cold classical Kuiper Belt object following the New Horizons flyby of Arakoth. The outer solar system remains, like Neptune itself, largely unvisited. The Kuiper Belt, enormous as it is, has been sampled by exactly 2 spacecraft, Voyager 2 passing through it en route to interstellar space, and New Horizons making targeted flybys of Pluto and Arakoth before continuing outward. Both spacecraft are now beyond the Kuiper Belt, heading toward the heliopause and the interstellar medium. Behind them, the Kuiper Belt continues its slow orbital dance around the Sun, undisturbed except by Neptune's distant resonance tugging and the occasional collision between its members that breaks one object into 2 and sets both on slightly different trajectories. And at the inner edge of the Kuiper Belt, Neptune orbits in its 4-hour radio silence, its winds blowing at speeds no instrument is currently measuring, its rings slowly shifting, its inner moons tracing their small, quick orbits around a planet that has not been visited by a spacecraft in more than 30 years. The distance that makes Neptune so scientifically isolated also makes it scientifically rich. Everything about it is uncertain in the details. The atmospheric dynamics that produce the extreme winds are not fully modeled. The internal heat source that drives the dynamics is not definitively identified. The magnetic field generation mechanism is not confirmed. The composition and structure of the deep interior are inferred rather than measured. For every confirmed fact about Neptune, there are 10 open questions. For every open question about Triton, there are 10 more that have not yet been clearly framed. This is not a failure of planetary science. It is a consequence of distance. The same distance that makes Neptune hours away by radio signal and over a decade away by spacecraft, and fundamentally difficult to visit, is the distance that has preserved its mystery. No swarm of orbiters has mapped it in detail. No atmospheric probe has descended through its cloud layers. No lander has touched any surface in the Neptunian system. Neptune is the last planet, not only in distance from the Sun, but in the completeness of human knowledge about it. It is the place where the solar system's inventory of explored worlds ends, and the inventory of unknown worlds begins. Beyond Neptune, the Kuiper Belt extends to 50 astronomical units. The scattered disk objects reach to hundreds of astronomical units. The hypothetical inner Oort cloud begins somewhere beyond that, and the Oort cloud itself, the vast spherical shell of comets that surrounds the solar system, extends perhaps a third of the way to the nearest star. All of it lies beyond the last planet. All of it has been touched, at most, by passing spacecraft that could not stop. Neptune is the sentinel, the last familiar landmark before the solar system gives way to the deep outer dark. Standing conceptually at Neptune's orbit, looking inward, the 7 inner planets are visible, distant but locatable, their positions calculable to arbitrary precision. The architecture of the solar system makes sense from here. The rocky inner planets, the asteroid belt, the gas giants, the ice giants, and finally, the vast cold space beyond. Looking outward from Neptune, Nothing resolves into familiar categories. The objects become smaller, more numerous, more distant, less well characterized. The solar system loses its orderly architecture and becomes a statistical distribution of icy debris, orbiting at distances and in configurations that resist simple description. Neptune is the last place where the solar system feels like a place. And Triton, orbiting Neptune in the wrong direction, with its geysers and its tholins and its slowly decaying orbit, is the last world in that last place, the most distant large moon in the solar system, the most recently captured, the most geologically surprising, and the least studied. The outer edge of everything, and yet full of science, full of chemistry that preceded life, full of questions that no instrument is currently answering, full of processes, orbital decay, seasonal migration, atmospheric change, geyser eruption that are occurring right now, continuously in the dark and the cold. The solar system's most distant significant world. Still active, still changing, still falling slowly toward the ring it will one day become. And waiting, not impatiently, not consciously, but in the physical sense in which any unexamined system waits, for the instruments that will finally arrive to look closely at what no human eye has ever seen. In the summer of 1977, 2 spacecraft left Earth within weeks of each other. Voyager 1 launched on September 5th, Voyager 2 launched 16 days earlier on August 20th. Despite launching second, Voyager 1 was placed on a faster trajectory and would reach the outer planets first. Both spacecraft were designed to take advantage of the rare Grand Tour alignment, the configuration of the outer planets that occurs once every 175 years, and allows a single spacecraft using planetary gravity assists at each stop to visit all 4 outer planets on a single mission without requiring propulsion at each flyby. The people who designed the Grand Tour trajectory understood when they committed to it what the geometry required. To reach Neptune with a gravity assist from Uranus, Voyager 2 had to fly past Uranus on a trajectory that carried it southward relative to the ecliptic plane, the plane in which most of the solar system orbits. From Uranus, the trajectory to Neptune took Voyager 2 further south. By the time the spacecraft arrived at Neptune, it was approaching from above the ecliptic plane, descending southward as it made its closest approach to the planet. This trajectory determined everything about what Voyager 2 could observe at Neptune and Triton. The geometry of the flyby, the approach angle, the closest approach distance, the declination of the trajectory, was fixed years before the spacecraft arrived, determined not by what scientists most wanted to see, but by the orbital mechanics that made the Grand Tour possible in the first place. Scientists adapted their observation plans to the available geometry. They could not change the geometry to serve the science. At Neptune, closest approach occurred on August 25th, 1989, at 3:56 UTC. At that moment, Voyager 2 was moving at approximately 15.4 kilometers per second relative to Neptune. It was 4,950 kilometers above Neptune's cloud tops, closer than the spacecraft had passed any of the previous planets. The decision to fly this close to Neptune was deliberate. A closer approach to Neptune meant a more extreme change in trajectory from Neptune's gravity, which in turn meant a closer approach to Triton on the outbound leg of the flyby. Science had to choose, close to Neptune or close to Triton. The team chose both, accepting that the geometry would limit the time available at each, and that the trajectory optimized for one would compromise the observation geometry for the other. The Triton flyby occurred approximately 5 hours after the Neptune closest approach. Voyager 2 passed Triton at a distance of approximately 40,000 kilometers, close enough to resolve surface features as small as a few kilometers across, but far enough that only the hemisphere facing the spacecraft was imaged. In those 5 hours between Neptune and Triton, the spacecraft's instruments were operating continuously. The magnetometer was measuring Neptune's magnetic field. The plasma wave instrument was detecting electromagnetic emissions from the magnetosphere. The ultraviolet spectrometer was analyzing the composition of the upper atmosphere. The infrared instrument was measuring temperatures across the disk. And the cameras, the imaging science system that had returned spectacular images of Jupiter's Great Red Spot, Saturn's ring divisions, Uranus's polar cap, and dozens of moons across the outer solar system, were pointed at Neptune and then at Triton, capturing as many images as the data transmission rate allowed. The data transmission rate from Neptune was approximately 21,600 bits per second. A single uncompressed image from the imaging science system contained approximately 5 million bits. At 21,600 bits per second, transmitting a single 5 million bit image would take approximately 4 minutes. Over the hours of the Neptune and Triton encounters, the spacecraft transmitted hundreds of images, along with the continuous data streams from all the other instruments. The scientists on the ground, receiving the data with a 4-hour and 9-minute delay, worked through the night and the following days to process, analyze, and interpret what was arriving. The first images of Triton to be fully processed showed a world that no one had predicted. The surface was bright, brighter than anticipated, with an albedo significantly higher than the theoretical predictions based on Triton's spectrum observed from Earth. The color was pinkish-white, consistent with nitrogen frost tinted by organic compounds, but different in detail from the pre-encounter models. The cantaloupe terrain appeared in the images of the anti-Neptune hemisphere, distinctive, immediately recognizable as unlike anything in the existing library of planetary images, and clearly the product of a geological process that had not been observed anywhere else in the solar system. The smooth volcanic plains appeared, overlying and partially burying the cantaloupe terrain in some regions. And then, in the images of the southern polar region, the dark streaks. The team's discussion of those streaks, visible in the original images that came in during the encounter, moved rapidly from observation to interpretation to confirmation over the hours and days following closest approach. The streaks were consistent in orientation. They ran downwind. They emanated from point sources on the surface. Some images showed what appeared to be active plumes, dark columns rising from the surface and bending in the wind before dispersing. Triton was active. The announcement was made days after the flyby, after the data had been processed, and the team was confident in the interpretation. Active geysers on the coldest measured surface in the solar system, driven by solid-state greenhouse warming of transparent nitrogen ice. It was one of the most surprising discoveries of the Voyager program. And then the spacecraft moved on. There was no option to return for a second look, no mechanism to adjust the trajectory to revisit a particularly interesting region, no choice but to continue outward, away from Neptune, away from Triton, toward the heliopause, and the interstellar medium beyond. The encounter lasted hours. The analysis has lasted decades. Voyager 2 is now in 2026, approximately 20 billion kilometers from Earth. It crossed the heliopause, the boundary between the solar wind and the interstellar medium, in November 2018, becoming the second spacecraft to enter interstellar space, following Voyager 1, which crossed the heliopause in August 2012. In interstellar space, Voyager 2's instruments are measuring the density, temperature, and magnetic field of the material between the stars, the interstellar medium that fills the galaxy between stellar systems. The data it is returning are the first direct measurements of these properties from a spacecraft located beyond the solar wind's influence. The spacecraft that gave humanity its only close look at Neptune and Triton is now measuring the galaxy itself. Its power output continues to decline. Instruments are periodically deactivated to extend the mission. Engineers at JPL manage the spacecraft systems across a communication delay of more than 18 hours each way, sending commands that will not be confirmed for more than a day and a half. The expected operational lifetime of the remaining instruments extends into the early 2030s, after which the power supply will be insufficient to operate any scientific instrument. The spacecraft itself will continue traveling indefinitely. In approximately 40,000 years, it will pass within a few light years of a star called Ross 248. By then, every human institution that exists today will have been transformed beyond recognition. Every language spoken today may have changed beyond comprehension. The mathematics that governs Voyager 2's trajectory will not have changed. The spacecraft will arrive at its closest approach to Ross 248 on a schedule that the people who launched it in 1977 could calculate to within hours. The universe keeps better records than we do. The proposals for returning to Neptune have been developed, refined, and presented to NASA's Planetary Science Decadal Survey, the 10-year prioritization document that guides the allocation of resources for planetary exploration. The 2023 to 2032 Decadal Survey, published by the National Academies of Sciences, Engineering, and Medicine in 2022, ranked a Uranus orbiter and probe as the highest priority flagship mission for the coming decade, the first time an ice giant mission had received the top planetary science priority ranking in the survey's history. Neptune was not ranked second. The prioritization of Uranus over Neptune in the 2022 Decadal Survey was based on several factors: the greater scientific accessibility of Uranus due to launch window considerations, the availability of a favorable launch window in the late 2020s that does not exist for Neptune, and the broader scientific case for comparative ice giant study that could be begun at the nearer target. But the survey also explicitly noted the scientific importance of Neptune and Triton, and the mission concepts developed for Neptune, Neptune Odyssey, a flagship-class orbiter and probe concept, and Triton, a smaller Discovery-class mission focused specifically on Triton, remain in the scientific literature as detailed, technically mature proposals, waiting for the funding decision that would activate them. Neptune Odyssey, as designed, would be a spacecraft roughly comparable in size and capability to Cassini, the orbiter that studied Saturn from 2004 to 2017. It would carry a suite of scientific instruments for remote sensing, atmospheric science, and magnetospheric study, along with an atmospheric probe that would descend through Neptune's cloud layers before being crushed by the pressure, transmitting data until the end. The orbiter would operate at Neptune for at least 4 years, long enough to observe the planet through a significant fraction of its 16-hour rotation, to track atmospheric changes across multiple Neptune days and seasons, to map the magnetic field in detail, and to make repeated close passes of Triton. Repeated, not one flyby, repeated encounters, each building on the last, each returning to features identified in previous passes for closer examination. The science returned from such a mission would be transformative. The Trident concept took a different approach, a smaller spacecraft targeted specifically at Triton, performing a single Neptune flyby, similar in approach to Voyager 2, but with far more capable instruments, and a trajectory optimized for Triton science rather than the Grand Tour geometry. Trident was proposed as a Discovery-class mission, the category of smaller, cost-capped planetary science missions that includes missions like the Messenger Mercury Orbiter, the Dawn Asteroid Belt Orbiter, and the InSight Mars Lander. Discovery missions are selected through a competitive proposal process and must be accomplished for a cost of approximately $500 million. The Trident proposal was not selected in the most recent Discovery mission competition, in which it was one of 4 finalists. 2 other missions, Da Vinci Plus and Veritas, both targeting Venus, were selected instead. Triton was not visited. The window for observing northern summer on Triton, the seasonal event that will begin in approximately 2065, and represents a unique scientific opportunity that will not recur for over a century, narrows with each passing year that a mission is not launched. A mission launched in the late 2020s could arrive at Neptune by the early 2040s, with time to observe the onset of northern summer and potentially observe northern hemisphere geysers that have never been seen. A mission launched in the 2030s arrives later and has less time in northern summer. A mission launched in the 2040s arrives as northern summer is already well advanced. The window is not infinite. The seasons of Triton move on their own schedule, indifferent to funding cycles and mission selection competitions and the competing priorities of space agencies managing limited resources across a large and diverse scientific program. The night on Triton's northern hemisphere will give way to summer in 2065. Whether any instrument will be there to see it depends on decisions that have not yet been made. This is the situation at the edge of the solar system. A world of extraordinary scientific value, orbiting in the wrong direction, erupting in the cold, falling toward its eventual dissolution. A planet of extreme winds and a magnetic field generated in its mantle, with processes in its deep interior that experimental physics suggests include the formation of carbon crystals under pressure, a ring system faint enough to have been missed for decades after the planet itself was discovered. A history of formation and migration and gravitational interaction that records the early solar system's most turbulent period. All of it out there, right now. All of it changing. The winds are blowing at 2,000 kilometers per hour. The geysers are firing. The orbit is decaying. The seasonal frost is migrating from the southern polar cap toward the colder north, molecule by molecule, year by year, in a cycle that has been operating since before the first multicellular life appeared on Earth. And the last spacecraft to look closely at any of it flew past in 1989 and has been moving away ever since. The silence that began that August is now more than 35 years old. It is a long silence for a world this active. It is a long silence for a world with this many unanswered questions. It is, in the deepest sense, a gap that reflects not indifference to the science, but the simple, stark reality of distance. The outer solar system is far. The investment required to reach it is enormous. The time required to return data is measured in hours, the time required to reach it in decades. But the science does not diminish with distance. If anything, it deepens. Every year that passes without a dedicated mission to Neptune adds another year's worth of atmospheric changes unobserved, another year of Triton's orbit untracked at close range, another year of questions accumulating without answers. The scientific community has not forgotten. The mission concepts exist, the scientific case is made, the instruments that would fly on such a mission have been specified and in many cases partially developed. The people who would build the mission and operate it and analyze the data are working in planetary science laboratories right now, some of them devoting careers to the preparation for a mission that has not yet been approved. The outer solar system waits with the patience of a place measured in billions of years. The scientists waiting for it to be explored have rather less time. But the world itself, Neptune, dark blue and distant, its winds screaming at speeds no instrument currently measures, its rings shifting in their slow gravitational dynamics, is not going anywhere. Triton is going somewhere, slowly, imperceptibly, inward. But not soon. Not before any mission currently proposed could arrive. Not before the measurements that could pin down the rate of orbital decay, map the unseen hemisphere, determine the state of the interior, detect or rule out the subsurface ocean, and watch the northern geysers come to life could be made. The window is open. It will not be open indefinitely. The scientific window, the window in which meaningful comparative measurements can be made, in which Triton is still a coherent world with an active surface and a measurable orbit, and an atmosphere and a seasonal cycle, is the window of now. Now, meaning the next few decades. Now, meaning missions launched within the working lifetimes of scientists currently in their early careers. Now, meaning before the northern summer arrives and the geysers that have never been observed come to life in the dark hemisphere that no eye has ever seen. The outer solar system is not finished offering its discoveries. It is waiting, as it always has, for the instruments that can receive them. And on a night like this one, quiet, dark, the world outside still, the distance does not feel so absolute. 4.5 billion kilometers. Light takes 4 hours and 9 minutes to make the journey. But the knowledge of what is out there, the winds, the geysers, the falling moon, the mathematics of the future ring, the unseen hemisphere, the questions that decades of silence have accumulated without answering, that knowledge crosses the distance instantly. It is here, now, in the understanding of a universe that is never finished, never static, never simply what it appears to be from any single vantage point. Neptune is out there, at the edge of everything familiar, following its 165-year orbit as it has since the solar system formed. Triton is there too, moving backward through its orbit, closer to Neptune than it was yesterday by an amount too small to measure, carrying in its ice and rock the record of a capture that happened 4 billion years ago, and the promise of a ring system that will exist 400 million years from now. The solar system is not finished. Not at its edges, not at any of its edges. And the silence that separates us from it, the silence of distance, of unanswered questions, of instruments not yet built, and missions not yet launched, is not the silence of emptiness. It is the silence of waiting. The universe is patient. It has been here before humans arrive to observe it. It will be here long after any record of this moment has dissolved. But the questions it contains, the questions written into the orbital mechanics of a captured moon, and the atmospheric dynamics of a storm-ridden ice giant, and the chemistry of organic compounds forming in the cold dark, those questions are being asked right now by people who have devoted their working lives to asking them. And the answers are out there. 4 hours and 9 minutes away at the speed of light. More than a decade away at the speed of the fastest spacecraft humanity has yet built. Present complete and waiting in the ice and the nitrogen and the mathematical precision of a retrograde orbit that has been decaying for 4 billion years. There is a particular quality to the darkness at Neptune's distance that is worth sitting with for a moment. At Neptune's distance from the Sun, the solar luminosity, the total energy output of the Sun, is spread across a sphere of that radius. The intensity of sunlight at Neptune's distance is approximately 900 times weaker than at Earth's distance. A solar panel that generates 1 kilowatt of electricity in full sunlight at Earth's orbit would generate slightly over 1 watt at Neptune's orbit. 1 watt? The sun, which drives all of Earth's weather, fuels all photosynthesis, warms the oceans and the land and the air. At Neptune's distance, that entire engine of life is reduced to a faint brightness in the sky, indistinguishable in character from a bright star, providing barely enough energy to be measured by sensitive instruments. And yet, in that faint light, chemistry is occurring. Photons that have traveled 4.5 billion kilometers from the sun still carry enough ultraviolet energy to break chemical bonds in Triton's thin atmosphere, to drive the photochemical reactions that produce tholins, to sublimate nitrogen frost from the polar caps, and drive the seasonal migration of atmosphere from pole to pole. The sun's influence does not simply stop at some distance. It fades, it attenuates. But it reaches Neptune, it reaches Triton. It is responsible for the geysers that fire from the coldest surface in the solar system. One of the quieter lessons of planetary science is the reach of small energies over large timescales. The sublimation of nitrogen frost on Triton's southern polar cap, driven by sunlight 900 times weaker than what reaches Earth, operating continuously over the decades of Triton's southern summer. These are individually tiny events, single molecules transitioning from solid to gas, single photons absorbed and converted to heat in a dark substrate beneath transparent ice. The pressure-building fraction of a pascal at a time. But over years, over decades, over millions of years, those tiny events accumulate into measurable atmospheric change, into geyser eruptions, into the redistribution of hundreds of millions of tons of volatile material from one hemisphere to another. The outer solar system runs on patient physics. Small forces, long timescales, outcomes that seem impossible given the energy available, until the time available is also considered. The orbital decay of Triton operates on the same principle. The tidal dissipation that removes energy from Triton's orbit and deposits it as heat in Neptune's interior is at any given moment an almost immeasurably small effect. The change in orbital radius in a single year is a fraction of a millimeter. The heat generated is a tiny addition to Neptune's already enormous internal heat budget. But 350 million years of that tiny effect, accumulating, adds up to the destruction of a world. This is the nature of deep time. It is not dramatic. It does not announce itself. It operates through mechanisms that are, moment to moment, quiet, gentle, and unimpressive. And then, on the timescale appropriate to a solar system, everything has changed. The planets have migrated to new positions. The moons have been captured or ejected or broken apart. The rings have formed and dispersed. The surfaces have been reshaped by cryovolcanism and impact and seasonal cycling until no trace of the original surface remains. What exists in the present moment is the temporary outcome of 4.5 billion years of patient physics. What will exist in 400 million years will be the temporary outcome of 400 million additional years of the same. Neptune will still be there. Its 16-hour rotation will continue. Its magnetic field, generated in the conducting layer of its mantle, tilted 47 degrees from the rotation axis, producing a magnetosphere that wobbles dramatically as the planet turns, will continue to sweep through space. But where Triton's disk now moves slowly across Neptune's sky, there will be a ring. And somewhere in that ring, spread across thousands of kilometers of space, in a band inclined to Neptune's equatorial plane, the atoms that once formed Triton's sculpted plains, the nitrogen ice that sublimated into geysers, the tholins that accumulated over billions of years of photochemistry, all of that material will continue to orbit, degraded from a world into a cloud of particles, following the physics that governs rings as faithfully as it once governed the orbit of a captured moon. Nothing is lost. It is only redistributed. The universe is a closed system in the end. The matter that forms a world does not vanish when the world is destroyed. It changes configuration. It disperses. It becomes something else, a ring, a cloud, eventually particles that spiral into the planet's atmosphere and are absorbed into the gas. Triton will become Neptune. Not soon, not in any sense that has emotional weight in a human context. But in the long arithmetic of the solar system, the captured moon will eventually return to the planet that caught it, and the two will be one, and the memory of the world with the backward orbit, and the cold geysers, and the story of its origin in the Kuiper Belt will exist only in the mathematical record of an orbit that once was. The outer solar system holds these stories in its mechanics. It does not tell them quickly, but it tells them completely and with perfect accuracy, and in a language that mathematics can always translate. If this story moved you tonight, if the cold and the distance and the slow falling of a world that should not be where it is settled into something quiet in the mind, please consider subscribing to this channel. Leave a like, turn on notifications. It means the work can continue and the next story can begin. Sleep well. Neptune is out there right now. Triton is there too, moving in the wrong direction, as it has always moved, as it will continue to move for longer than any human scale of time can hold. Everything you heard tonight is real. Neptune and Triton are out there right now,